Good evening, everyone. We'll start the session by 4:05. So we'll wait for 5 minutes.
Bit more on the surface with spinners, but we could play just keep a little low, kept a little low. I thought we could play better than we expected.
It's a long series, just the first match, and your team is more than capable to come and fight back, isn't it?
Okay, I think we can start. Let me share my screen. Tajul, once again, am I audible as well as my slide is visible?
Yes, Professor Ashwin.
Okay, sir. Okay. Okay, sir. Thank you. Okay. Good evening, everyone. Welcome to this session where I will introduce you to IS 18168 2023. I'll give you a background of what that code is, etc. And I'll take you to the design of steel of moment resistance as per this latest code, which is available in the BIS site. Okay. So the introduction is in terms of IS 800, like with respect to design of steel structures, you may be already aware that we have been using IS 800 2007 for a long time. So in IS 800 2007 in section 12, you must be aware that there are 3 systems that they mention that we can use it in our steel structures, which includes moment resisting frame, concentrically braced frames, and eccentrically braced frames, right? There is a new code that has released, which is IS 18168, which released last year only, which is titled as Earthquake Resistant Design and Detailing of Steel Buildings Code of Practice, which again includes SMRF, SCBF, and EBF, And you might see the small difference between the section 12, wherein it is MRF, which includes ordinary moment resisting frame as well as special moment resisting frame. You can see the names in IS 18168 are SMRF and SCBF, which is special moment resisting frame and special concentrically braced frames, which means this particular code, which was released last year, was only focused upon high seismic zones, which means these three structural systems, if used in high seismic regions, what could be the kind of codal guidelines that needs to be done for the design of steel structures. Now, my aim here is, if you go into performance-based design of RCC structures, which Tajul and Vaising sir have already covered with you. Now, with respect to steel buildings, before we go into performance-based design, we don't have much of an information regarding how to even design them, right? So my aim today is to kind of make you understand what are the code clauses, how to design a particular structure, so that you can understand based on whatever information that you have gained till now to do a kind of vulnerability assessment. And if the performance is poor, you can go for a performance-based design. So the idea is to understand the current design guidelines and how to design these three systems, SMRF, SCBF, and EBF, in which we will be covering today the special moment resisting frames in totality. So what does the new code say? IS 1868 says that in zone 5, only EBF system can be used, which means a code recommends eccentrically braced frame in a high seismic region like zone 5, which means you can understand that an EBF system is a much more ductile system than the others. And it says special concentrically braced frame shall not be used in zone 5, which means there is some problem in SCBF. You can understand, we'll learn next week as to what the problem in SCBF is there, which makes it not suitable for zone 5, but okay for zone 4, 3, and 2. And then in this code, IS 18168, it says that in zone 5 and zone 4, SMRF for buildings less than 15 meters, you can use this particular code to kind of design these structures. So it is like SMRF ke liye, in zone 5 and 4, if the building's height is less than 15 meters, then only you can use this to design SMRFs. Clear? Now you already know this particular image with respect to the capacity design, that you understand that when you look at this particular chain of like links which are connected with each other. In capacity design, what we mean is that we design the weakest member to be the most ductile member. So my deformation performance and everything is dependent upon that ductile member. Whereas the non-ductile or the brittle member is made the more stronger one, which means what we are claiming to do is we identify a certain member in the structural system, which we intentionally make it weak, but also make it intentionally use the correct material to make it more ductile, such that maximum amount of energy dissipation, which is like going into the nonlinear region and the area under the nonlinear curve, is what we call as the energy dissipation, which we need during an earthquake, such that rest of the system like beams and columns, like if you're looking at a moment frame, we need to identify which element we need to make it more ductile and which can be less ductile and more stronger, such that my maximum energy dissipation happens in the beam. So such a way we have to identify which member is more ductile and which member needs to be more brittle, such that there is a hierarchy in the performance of the system, and maximum energy dissipation happens in that member whose damage or total fracture does not hamper the gravity load carrying capacity of the system, right? So we have these three systems, that is SMRF, SCBF, and EBF system. So in an SMRF system, what we mention is that we have to identify which is the ductile member or the weak member that we have to go for, in which we can name it as, you can read many textbooks where these names of ductile and brittle member, rather than saying it as brittle, we say the middle link that you see here as a deformation controlled element, and the brittle element symbolically, which is shown here, is given the name force controlled element. So in an SMRF system, we mean that the beam is the deformation controlled element, shown in green color, where we want the energy dissipation to happen. Now you can think that if I consider an inelastic deformation, or maybe Tajul has already covered in terms of plastic hinges being formed, which means extreme fibers are getting yielded, and that the fiber is moving from the exterior fiber to the whole section is getting yielded, where the plastic hinge is getting formed. So through that, we want to dissipate energy, and that hinge has to have adequate ductility or rotational capacity, such that it allows the deformation in the member. So when we say that we want energy dissipation to happen in the beams, we know that if a column mechanism occurs, you can see in this particular frame that if I say if the hinges are forming in the columns, 4 hinges are more than enough to create a column mechanism which is unstable. You know that it's a soft story kind of a behavior may be brought out. But if we have plastic hinges in the beams getting formed through design, that we design it in such a way that the hinges are getting formed in the beams, then we have maximum energy dissipation in the system, right? So it is about identifying who is the more ductile member where we want the energy dissipation to happen. You must have already understood that, okay, if hinges are forming, nonlinear hinges or yielding is forming in the column, it means that the column will get damaged and that can lead to collapse of the member. Whereas localized plastic hinges at the beam is not that kind of a problematic that we have learned earlier also. In case of an SCBF system, which we'll learn next week, is the ductile member, the deformation controlled element are the braces, which undergoes yielding and buckling under compression and yielding under tension and dissipates the energy. Whereas the force controlled elements are the beams and columns, which means anything. It's like an electric fuse in your house, that whenever the power or voltage increases, the stabilizer or the fuse element gets blown off, safeguarding all your electrical equipments. The same way, if the braces gets damaged in yielding or under buckling, whatever happens, it dissipates the energy during the earthquake, safeguarding the beam column element. So the deformation control in the braces in the CBF system is the braces, and the beams and columns are the force controlled element. Now, regarding the eccentrically braced frames is intermediate to a moment frame and a brace frame, where you can see a slight eccentricity in the center line of the braces, right? There is a small element, a link element, which we call as a link, which we'll cover next week. This link element is the energy dissipating element, which means the brace, which was supposed to yield and buckle in a CBF system, is supposed to remain elastic throughout the performance of the EBF system, whereas the whole energy dissipation, either through flexural hinges or through shear hinges, is formed in this particular small location, which is termed as the link element. So the big takeaway from this particular aspect is that IS 18168 works on the principles of capacity-based design, where we identify a deformation controlled element and we identify a force controlled elements. And the deformation control element is given the whole onus of dissipating the inelastic energy during an earthquake, undergoing yielding, undergoing buckling, and all sorts of nonlinear thing that it can undergo, while safeguarding the force controlled elements like beams and columns in a moment resisting frames, beams and columns in a CBF system, beams, columns, and braces in the EBF system, right? Your design, whatever you are learning as per IS 800 2007 with respect to designing of beams, columns as per limit state method does not change. It is only a hierarchy that is being brought through the capacity based design method, through which we allow a certain duty to certain elements and give another duty to force control element. That is the whole difference between what 18168 brings to the table, right? Now, the first thing that we have to understand with respect to 18168 is, okay, if I start a project, if I start a design with respect to a moment resisting frame, CBF or an EBF system, what material grade should I select for the design, right? So as per 18168, if you download that particular code, you will understand that it crystal clear in a way makes you understand that the sections, whether it is rolled steel sections or plates, can be of grades E250, 275, 300 and E350, right? So earlier I have a slide. I mean, in this slide itself, you'll get to know what the earlier IS 800 used to give. So currently you can understand that as per the new code, you can use grades up to E350, right? Another clause inside the same code says that if any other steel is being used other than E250, 275, 300 or 350, you have to ensure that the yield stress, the nominal yield stress should not be greater than 350. So currently the code in a high seismic region does not allow you to use more than a 350 grade of steel, right? The second thing that any other class of steel, which is not per se of the grades that are mentioned above, if you use, it should have a minimum elongation of 22%, which means you do a coupon test as per IS 1608 or ASTM EA. You mark the gauge length location, and then finally, once the failure has happened, the fracture has happened, you measure the change in length to original length of that particular gauge length area, gauge length location. So that particular change of percentage elongation should be more than 22%. The second requirement that the steel should have, it should have a minimum Charpy V notch impact value of 27 joules at 0 degrees Celsius. Now, I'll make you understand this thing. And the third criteria that it says is that there should be a ratio of ultimate strength to yield strength of the steel should be minimum 1.15. Now, you have to understand that all these three clauses that I've mentioned directly from the code, which is related to percentage elongation, this one, the Charpy V notch test requirement, as well as the ratio of FU by FY, which was earlier there in IS 13920. If you check for RCC, for reinforcement bar, this clause was earlier there, but this has also been introduced in this particular code as well. Now you have to understand, let's start with the bottom one as to what 1.15 of FU by FI greater than 1.15 gives you. If you take a beam section of a moment frame, and then you have a grade which you use where your nominal grade, nominal yield strength is 250 MPa, and you have a FU, nominal FU, which is nominal ultimate strength as 450 MPa. If there is a high ratio, 450 to 250 is a very large ratio that you have. If you have that part, then when the yielding starts, the moment one extreme fiber reaches 250 MPa, and then you can take larger amount of yield strength because its ultimate strength is 450 MPa, more area of the beam undergoes the yielding, particularly in that zone. The zone length, the plastic hinge region increases, which means the beam can undergo larger rotation before it fails. If the ratio is too small, then it has lesser rotational capacity, and it will quickly, every fiber will yield very quickly. Let's say 250 is the nominal, and let's say 280 or 300 is the ultimate. You can understand that by that time, the whole region is going into this particular region of non-linearity. It will go quickly in the case where FU by FI is low, and where its gap is larger, the beam is allowed to undergo more rotation, right? The second part, which is respect to Charpy V notch, is another value which we normally tend to think as if, why does the code give a Charpy value, which is like, if you think about the Charpy test, it is just an impact, it is just the energy dissipation, or you have a Charpy small V notch that is made, and then a pendulum drops in, and then it impacts the V notch, and then you measure amount of energy that is dissipated or stored in that particular notch. That is the way we represent. Now, the meaning here is, if there is a crack or if there is a deformity in the plate material, when it undergoes non-linearity, this particular property of Charpy V notch, having an energy of 27 joules at 0 degrees Celsius, ensures that your steel doesn't crack very quickly. Like if there is already a flaw there, which normally the steel tends to have, either in the welding region or in the base metal, it may have certain kind of deformity, a crack during welding or something like that. But what happens is, if this property is getting maintained, then the amount of energy like the steel material has does not allow the propagation of the fracture to happen very quickly. So that is why you can say, okay, why does the code only give 22% as the only criteria? You can understand now that, okay, these are for different things, and for an earthquake kind of condition where you know that we design the structure for a response reduction factor such that we are dependent upon the nonlinear performance of the element. We need these kind of properties to be there in our steel such that it gives a ductile performance, right? So three criteria: percentage elongation, Charpy V notch results, as well as the ratio of FU by FI. Now the next is, if you remember, in IS 800 2007, the older version of 18168, you must have seen that clauses. What I picked up from CBF system is that you can see bracing members shall be made up of E250B steel of IS 2062. IS 2062 is a code where the grades of steel, their mechanical and chemical properties are given. So here it is clearly mentioned in the older code that you should not go beyond E250B, right? Whereas the new code gives you E350. You can go up to 350 MPa. Whereas in special moment resisting frame also, it was mentioning IS 800 2007, it was E250B was the only value that was given. But remember that in January 2012, an amendment came for IS 800 2007, where it was mentioned that bracing members shall be made. There was an amendment made that this particular clause 12.8.2.1, a particular statement needs to be added that bracing members shall be made of E250B steel of IS 2062 or of steel having Charpy V notch energy greater than 27 joules. which means before 2012, yes, across India, the maximum grade of steel or the maximum MPa of yield that was allowed, nominal value, was 250 MPa. But by the involvement of this particular line of steel having a Charpy V-notch energy greater than 27 joules, it opened up a possibility for steel makers and manufacturers to have steel of E greater than 27 joules or even higher strength. So if I show you IS 2062, which I said involves the chemical, it highlights the chemical and mechanical properties of the structural carbon steel that is available in India. First of all, you can see that the grade is from E250 to E650, but currently our code limits our use of grade of steel to E350 only. So when you see E250, whereas E350, the minimum Charpy V-notch energy at 0 degrees Celsius, it is mentioning it as 27 joules to be minimum. So consider one thing that, let's say after 2012 amendment, we could have even used E350 in our code, but many people don't know this particular fact, or they ignored this particular fact to be clear. So there is a limit that, okay, before 2012, E250 was the highest grade of steel that could be used. After this amendment in January 2012, yes, we could have gone into E350, provided the steel makers would have given us that particular steel on request. But now from current onwards, IS 18168 clearly mentions that you can use up steel grade up to E350, right? So you can understand, okay, you can understand one thing, that E350 is, as I earlier said, 18168 is only for high seismic region. Whatever grade or whatever structure that we mention in high seismic region can be also used in a low seismic region also, because you understand that the demands in high seismic region is very high. The performance of these systems are much better than what there is there for the low seismic region classification. So you can use these kind of grades there also, right? So the big takeaway from this particular slide is that we can go up to E350, right? So this is IS 2062. I request all of you to go through this particular code to understand what are the different grades, what are the different classifications, what is the chemical composition, etc. Now this is a new entry into IS 18168. We understood that capacity design is the main heart and soul of IS 18168. Now, if capacity design is there, we have to identify the weakest member, and based on the maximum force that the weakest member can transfer to the brittle member or force control member, they should be designed accordingly. So IS 18168 has introduced a factor known as a material uncertainty factor, which is nothing but you have two factors that is given. One is Ry, which is the expected yield stress to the characteristic yield stress, which is not what you test. Like if I give you a plate in hand and I say this is E350 grade plate of 16 mm thickness, and I tell you go and do a coupon test and tell me what is the yield strength that you are achieving as well as what is your ultimate strength that you are achieving. So Ry is the value of the yield strength value that you get from the coupon test divided by the nominal value, which is if you use a nominal grade of 350 MPa, test it under coupon test, you obviously believe that 350 is the minimum yield strength that is mentioned by the code. So obviously the material would have a higher strength, let's say 400. Like when you test it, you get an yield strength of 400 MPa, whereas the nominal value is 350 MPa. So 400 by 300 is the value of Ry. Whereas Ru is with respect to the same ratio with respect to the ultimate strength. So whatever expected value of ultimate strength is there divided by the nominal strength mentioned by the code for that particular grade. The relevance is very important here. First, let's see what is the table here. It says E250 means Ry is 1.4. You can, let's look at only the Ry factor here. So we have E250 grade 275, 300 and 350 as per the current code. Yes, our limit stands here. You can see that as the grade strength is increasing, as the grade is increasing, like E250 is a grade of nominal yield of 250 MPa and E350 is for a 350 MPa. You can see how the variation goes. So if it is a low grade steel, the Ry value or the uncertainty in the nominal yield strength or the yield strength value is going to be much higher than what you have for a higher grade steel, right? Its relevance will come at a later stage in terms of what importance it is or what the danger of using E250 grade was there and what the E350 grade is going to be, right? If you have any other steel other than E250, 275, 300 and 350 but less than E350, then for that particular steel, you can use a RY value 1.4 and 1.2. This is a value that the code says that if you don't have much of an information regarding the grade of plate that you have, kindly consider the higher end values in terms of RY and RU, right? As I already mentioned, this value will be used to design the force controlled element, as this uncertainty value will be used upon to calculate the maximum capacity of the ductile member, which is, if I'm designing the beams will be designed as such with respect to the limit state procedure. Once I have got a cross section, what is the maximum bending moment that cross section can take will depend also upon the RY value, right? It is the expected value that I'm looking at. So when I design my columns, which is the force protected element or the force controlled element, I have to get what is the maximum capacity of bending moment that can be transferred from the beam, and there this R value will come into play. So this uncertainty factor is not for the design of deformation controlled element, but it is to understand the maximum capacity of the deformation controlled element so that you can design the force controlled element. I hope it is clear to every one of you, right? So we have done few tests at our place in terms of understanding what if we use for a higher grade of E450. This is just for the information that maybe sooner or later the code might transition into E450 grade also. So you have to understand that this ratio RY uncertainty factor, when it goes to E450, it comes down to 1.1 only. Now you have to understand that this R value, RY value or RU value is kind of an average value. And when the grade capacity or the grade strength increases, let's say E350 to E450, as I mentioned, this RY value is only 1.1, which means you have less uncertainty in the material that you are using, which makes that particular grade of steel more kind of prominent to be used in a high seismic region, right? So the catch here is, as soon as high strength steel we go, yes, ductility decreases, so all other problems come in. That is why the code does not recommend anything beyond E350. But if you look at only the material uncertainty factor, then E450, if it had enough ductility, would be an ideal choice, because the material does not have uncertainty over its yield strength or its ultimate strength, because that is where the capacity design. So if you can understand, let's say I have a E250 beam connected to, let's say, an E250 column. You can understand that the beam section might be different, the column section might be another section, and the heat input while manufacturing or the rolling process or the cooling process of these two beams might be different. So since this is an average value that is given there, you might find that the beam might have an RY value 1.4 as per the code, but if you test a coupon, you might get 1.5 also. So there is a problem that if my RY value is not under control, or if I don't have a proper estimation of that particular RY value, rather than ending up with a strong column weak beam, I might end up with a weak beam, weak column, strong beam kind of a situation. So that is why this quantity, for the design purpose of creating a hierarchy between deformation control and force control, is important. Also, it is important to have a total control as to when you give your orders to a manufacturer of steel. You have to ensure that, okay, you're giving me the average value that is given in the code, but kindly do some testing and give me a mill test report also. Let me do some testing at the lab also to ensure that 1.4 is a good number to go with or not. Right? You understand now the clarity. Just to summarize, RY factor or the material uncertainty factor is for designing the force controlled element only. It is not for the deformation controlled element. The deformation controlled element ka maximum capacity we need in order to design the particular column element in a moment resisting frame, which is the force controlled element. So we have to apply this uncertainty factor while calculating that demand value from the beam so that I can design the column. So that is the whole deal of the uncertainty factor. Now you must have all seen this particular image wherein it is a moment rotation curve of different class of sections, where the classes of sections are compared as slender, semi-compact, compact and plastic. You must be also remembering table 2 in IS 800/2007, which used to mention that, okay, if my B by T, width to thickness ratio of the flange, or depth to thickness of the web ratio, if it is less than a certain value, I can classify it as among or either of these particular categories. Now, among these categories, I want to make you understand that, or maybe you already know that, the plastic sections are the much better section which has to be used in a high seismic region, where I expect nonlinear hinges to get formed, and that particular section should have adequate rotation because the demands are also very high. So a plastic section is the most ideal section which dissipates maximum amount of energy and has enough rotation to kind of accommodate whatever the demand the earthquake gives. And the slender section does not even reaches its yield value. Such sections do not reach yield and undergoes local buckling before it fails. Right, so you have such kind of sections. So you can see the extreme fibers have reached the yield here. So a semi-compact section may yielding allowed hai, but it does not achieve its plastic moment capacity and does not have enough rotation also. A compact section achieve the plastic moment capacity but does not have enough rotational capacity. And then you have the plastic section which behaves very well, right? So such a classification was already given in table 2. But what you have to understand was that if you look closely at table 2 of IS 800 2007, you will see that the whatever requirement was given there for beams or columns or built up section, etc., was largely for flexural members, like in a moment frame beam or a column. Plus, if you compare the value given in that particular section and compare it to international codes, you will find that we were a little bit more relaxed about the requirement of plastic section or semi-compact or compact section. So the current code, this particular table is again table 2, but of IS 18168, right? This one again gives what is the width to thickness ratio. You have to go for a beam, a column, a brace, and a link element. I hope you remember links are for EBF system. This is for brace of a concentrically braced frame. Columns are columns, beams are beams. Now you can see, since this is a high seismic region, whatever this particular this thing is given is similar to for a plastic section. So if you satisfy this particular limit, then you are achieving a plastic section in totality. Now, just for the information of everyone, if I have a beam, if the flange satisfies the plastic condition and the web satisfies only the compact condition, then the section classification is compact. So if I want to have a plastic section in totality, then my flanges as well as my web of my section in a beam or a column should be plastic in total. So that is what this is given. But what is the whole purpose of giving this compactness ratio is to avoid such kind of phenomena. So you can see here an image where you have a beam column joint, and in that beam column joint you can see that, okay, let me identify for all of you, this is the beam, right? In this particular beam you can see the web has been welded to the column flange, the beam flange has been welded to the column flange at these two locations, right? There is this column, a thicker column with a thicker flange thickness that is there, and then you have these two plates that are given as a stiffener, as you call them, but in IS 800 or IS 18168 language, this is known as the continuity plate, right? We'll come to this particular part as to what continuity plates are. There is a story entirely on this panel zone, etc. But what you can see is this is a test of a beam column joint wherein you can see the yielding of the member has happened. Normally, when we do test here, we put whitewash on top of the plates, or we put strain gauges on top of them to understand the profile of the yielding. So you can see here the whitewash has gotten removed. It doesn't say when it has got, because then you have to use a strain gauge to get the exact moment at which the strain has gone beyond the yield value. But if you put a whitewash, the flaking of the whitewash shows the certain profile in which the yielding has occurred here. Now, our concern regarding table 2 is not with respect to where the plastic hinges form. Our concern is with respect to this particular phenomena that is happening at the top of the flange of the beam. This is known as, I hope everyone knows, this is local buckling. Buckling in a very localized area. So local buckling is what the terminology is. So our whole purpose is, if you look at a hysteresis curve of a beam or the plastic hinge or the moment rotation curve like phenomena, you'll know that once the beam undergoes yielding that reaches the plastic section capacity, it achieves maximum rotation only if the local buckling phenomena is delayed. I'll repeat. A beam which is destined in a moment resisting frame to undergo yielding in the plastic hinge region here is destined to yield at the extreme fiber, then achieve the plastic moment capacity, then have adequate rotation, like a plastic section should have, only if the phenomena of local buckling is avoided, right? That if I can totally avoid the local buckling, it will have a longer life. But normally what you can understand is when the yielding happens from the extreme fiber, there is always a nonlinear yielding, means there is a permanent deformation that is set in the members. So when the deformation increases or the nonlinear deformation and the demand increases, obviously there is some permanent set is going to increase. So that particular length of the member is going to get buckled very easily, right? So this particular table that is given in IS 1800 as well as in IS 18168, main purpose is to delay the onset of local buckling. So when you look at this particular kind of criteria, it says beam outstanding flange width to thickness ratio should be less than this particular value, means your design might have already told you that 12 mm thickness of the flange is good enough. But this particular criteria, what it does is it makes you give even more higher thickness of the flanges, which means when the beam undergoes yielding and etc., the thicker flange does not allow the easy local buckling of the member. So please understand that even though this is for compactness ratio, in order to make the section achieve maximum plastic moment capacity, whatever plastic moment capacity, maximum rotation capability, the main idea is to delay the onset of local buckling rather than avoiding it. The same problem is with brace frame also. You can see the phenomena of brace frame. The brace is buckling here. Then the local buckling, you can see a dip that is formed in the brace when the nonlinear deformation increases. Then there is fracture initiation that starts, and then the final fracture happens. So if you choose a brace section, which is a very, what do you say, not so stout section, which is like having a large diameter and a very small thickness, you can understand that that particular section, when it undergoes buckling, in terms of buckling or yielding, it is going to undergo larger local deformation than a stout section. If a member undergoes global buckling, is anyway part and parcel of the life of a brace element in a concentrically braced frame. So if global buckling along with a higher amount of local buckling occurs in a brace, the brace fractures much earlier. So when you have capacity elements like beams and deformation controlled elements like beams and braces in a CBF system, which you want to have a longer life such that you can achieve that ductile performance as the weakest link with more ductility, you don't want any premature fracture to happen. So the next thing is, apart from the selection of the material, the compactness criteria has to be maintained so that you can delay the onset of local buckling in the member. Now coming to our topic with respect to moment frames. So you have understood 18168 में क्या-क्या देते हैं. We'll come to specifics related to moment frames in these later slides once we understand what a moment frame is, etc. So I can take the questions at a later point, but we can start with moment resisting frames. So the first moment resisting frames was built in Chicago in 1884, wherein you can see the type of connections that they were building at that time. So you can see how redundant these connections were. More than required size of plates, more than required size of bolted connections, and all those kinds of higher redundancy or higher strength was assumed in terms of design, and then it was built. And you can understand that the Empire State Building, you already know this particular building, where for the first time rolled I and H sections were used in the design. Post World War II, for some reason, when they used all steels, etc., they tried to optimize these kind of connections into a more uniform one, which we normally see. So you can see a 1970 welded flange bolted web connection, which we normally see in India as to what these sections. I mean, when we go outside in India with respect to beam column joints, we normally see this kind of a connection where we bolt the webs as well as weld the flange. So again, once again, you can see the continuity plates here, right? You can see the continuity plates at these two locations. It's a stiffener, right? So what does the property of the continuity plate does is, like if I have bending moment, if I have earthquake, or if I have gravity loads wherein this particular flange is going to give compression to the column flange here. If the column flange is of a larger width, then it can undergo local buckling quickly. So to stiffen that particular flange of the column is why we give the continuity plate. Another name as we go ahead in moment frame, हमारा introduction हो रहा है moment frame की तरफ. So we have to understand one more thing is, there is a doubler plate that is also used in the web location. That is, you can see the panel here, right? The web of the column in between the column flanges, which is in between the continuity plates, where the high amount of shear force is getting generated. So to avoid shear buckling, the early shear buckling, a doubler plate, which is like additional steel plate is welded to the front and back of the web of the column in this particular area, which is known as a doubler plate. So a moment frame has very few number of elements that has to be designed. One is the beam, obviously, one is the column. Then you have a panel zone, which is this particular area confined by the column flanges and continuity plate. and then there is the connection. Now, what you have to understand that in US and across the world, during 1960s and 70s, there were many tests that were done in terms of assessing, you understand the capacity of your beam through, let's say, a 3-point bending test or a 4-point bending test. You understand the capacity of your columns through, let's say, a column compression test with some lateral load provided. So you understand the capacity of those sections, but then connections were also treated in most importantly before a certain event that I'm going to explain now. So many tests were done with respect to beam column joints and many connections were developed. But there is an event in 1994 which you can read about, which changed the whole path of in which the steel frames were being designed, which is a 1994 Northridge earthquake. So you can see here in this particular image is a kind of typical damage that was observed in a steel structure in 1994 Northridge earthquake. You have to understand one thing is that in 1994 Northridge earthquake, none of the steel buildings collapsed, which also shows the way in which these steel buildings or structures made with steel are much superior to what an RCC building is there. But to say that okay, nothing collapsed, but there were certain locations of failure that were observed in the frame members. So you can see this is the column flanges. This is the beam bottom flange that is shown there. This is the beam web that is there. This is the continuity plate, and rather than a doubler plate, the shear panel in the panel zone has been stiffened using a vertical stiffener plate, right? The same process, like if I want to stiffen a panel zone, I can either give a doubler plate or I can give it by the stiffener, which divides the panel zone into two different areas, reducing its shear buckling length, correct? So you can see column and beam here. You can see the weld access hole. So, and you can see a crack that is emanating from the bottom of the weld flange directly across the column. So what happened during at that time was that they noticed that you can see a small thick plate below this. So you have a weld access hole where people would be giving complete joint penetration weld here. So when they were doing the welding, they would give this backing plate such that this particular weld does not oozes out. But the process earlier was to keep this backing plate in place, thinking that it will reinforce that particular joint area. But later on, it was understood that by keeping the backing plate, it creates a deformity or a flaw in the welded region, such that when earthquake or a cyclic load is applied, this translates into a crack or a failure in terms of the functionality. So yes, none of the steel buildings failed in 1994 Northridge earthquake, nor in the 1906 San Francisco earthquake. So you can see the area of San Francisco after 1906 San Francisco earthquake, which prompted people to initially use steel structures in US and Japan because steel was showing much better performance. Whatever building standings were steel structures, whereas the RCC and masonry structure fell all around. In 1994 Northridge earthquake also, if you read about it, the steel building did not collapse and the RCC and rest of the buildings performed very poorly. So what were noticed during the 1994 Northridge earthquake is large beam and column sections which were not tested. Like why I'm saying all this is to understand what flaws we as Indians have with our steel grade and our steel research is there, so that practitioners, students, or who are doing PhD or masters can look into more of this area in terms of improving our design code as well as our design practices. So what was noticed that whatever the beam or column section that was being used in the buildings were not the ones that were tested. The ones that were tested were of smaller size. So size effect as well as the kind of conditions that can have if you have a larger beam section was not treated well during the testing procedure. And then the welding detail, you can see all rest of the three details as to the reasons of why failure happened during the 1994 Northridge earthquake was related to the welding being poor, or the conditions. Welding electrode material was not good, high stress strain at welded connection because of the backing plate that was there, and poor welding details were all the reason that was there, right? So this again, this particular thing comes in. This one gives you a better name in nomenclature, joint penetration butt weld that is there. This is the beam, shear tab, continuity plate, and if continuity plate के बीच में यहाँ पे इस area में I can also give a doubler plate. So these are the common elements that are there in a moment frame, and when you design, these are the elements that come into picture. So this is an ideal hysteresis curve. Now hysteresis curve is nothing but the load deformation curve of an element or a sub-assemblage which have been tested let's say into the non-linearity. So you can see in tension and compression, this particular element, this beam element has been tested, and you can see again that the yielding has happened, and finally, irrespective of what the size of the element is, local buckling is bound to happen. But our requirement is that within the range of demand that the earthquake is going to give us, like normally if you open any FEMA code, etc., it says, okay, under DB level, the interstory drift ratio for a moment resisting frame should be below 2.5%, whereas under MC level, the interstory drift ratio value should be less than 5%, because beyond 5%, nobody can guarantee the the efficiency of the connections. Beams and columns may be functional, they might not have fractured at all, but dependability on the connection reduces. That's why beyond 5% we don't go as per the total capacity of the system. So if we can prove that the hysteresis curve does not drop below a certain strength value for the range of demand, let's say 5%, then everything is fine. Local buckling is bound to happen. So B by T ratio, D by T ratio is just to delay the onset of local buckling in the member. So what they did is what the Americans did after 1994 Northridge earthquake as a solution to whatever failures that were observed in the beam column joint. They came up with a code. So many of you might be knowing this particular code, or the students who are attending this particular course, I would request them to open this particular code, download it. It is AIC 35816, which is a code for pre-qualified connections. So what they did after that is they had already done a n number of tests on connections and found that it had a flaw. Then they rigorously started testing it even further, understanding what were the flaw as listed here. They created procedures for welding. They create as a WPS and AWS document that you find. And then they created this particular different types of pre-qualified connection, which I'll show you later. This is one of them, but I'll show you different pre-qualified connections that are available out there for which they have given the procedure. Now, one particular note that you have to understand is this particular procedure that is given in 358 is what they have understood about their material, and they have quantified its performance or guaranteed a certain performance in a certain seismic region. Copying the same procedure for our place is fine, but then we have to understand the limitations of our material, like the factor RY factor. The steel that Americans use is A992, in which the RY value does not go more than 10%. So you can understand that when you are testing your steel for their procedure, you have to understand, maybe if you're using E350, your RY value is 1.2, or if it is E250, it is 1.4. So the whatever earlier I said, we have to take care about strong column, weak beam, not turning into a weak column, strong beam kind of a condition, right? So as a moment frame, what do you expect in a high seismic? I mean, we are talking about performance-based design. We need to understand what is the ideal performance from the system. So as in a moment frame, we say that, okay, if I get, as I explained earlier, if I get maximum hinge mechanism in the beams, then I'm dissipating more amount of energy, which is ideal for my system. And I can also kind of be happy with having plastic hinges at the, or yielding at the bottom of the column also is acceptable. Right? This is the ideal mechanism. If I go for only column hinges or the column mechanism, then you understand that rather than having so many hinges, my hinges might be only concentrated at a particular floor level, and the building can undergo collapse. So this is the ideal mechanism, that formation of plastic hinges at the ends of the beams and formation of plastic at the end of the base columns is the ideal behavior. While this is happening, once again, local buckling of beam and column flanges can happen. So it is not nothing new that if you find this kind of local buckling, it is meant to happen in a beam. And large deformation of the web can also happen when the demand increases. It's not under serviceability, not under DB, but this is a condition when the drift reaches a higher value, let's say an interstory drift ratio of 5%. Then only such kind of a heavy deformation in flange and this thing is expected. Now, if I look at, as I explained in the last slide, what is a favorable behavior? Let's look at what is the unfavorable seismic behavior. For a beam, excessive local buckling can result in strength loss and ultimate fracture associated with low cycle fatigue. You understand why I call it low cycle, or to be precise, we should call it ultra low cycle fatigue, because in an earthquake, only 10 to 20 cycles are more than enough to fracture the member under fatigue. So let's call it ultra low cycle fatigue. So what is the remedy if I have excessive local buckling? I have to choose a highly compact section as per table 2 of IS 18168. Also, wherever lateral bracing, this lateral bracing is horizontal bracing that is given to the beams or the columns in order that they have some bracing in order to increase their capacity, reduce the sway action moment. That is why this is like, okay, you have to give highly compact section in the sense, not in the sense of table 2 में compact section के case में, it is like giving a section which achieves plastic moment capacity and has adequate rotation, which means a plastic section, right? And then the problem, unfavorable behavior in terms of connection would be fracture in and around welds, fracture in highly strained base material, fracture at weld access hole, net section fracture. Fracture in weld access hole is just the hole that you saw near that backing plate that is there, which is like, which gives an access for the welder to do a CJP welding along the flanges. So sometimes people cut that hole also to give him the easiness of welding the particular flange. Net section fracture of bolt hole, shear and tension failure of bolts, bolt bearing and block sheet failure. These are all names which are associated with connection failure. And the remedy is to give pre-qualified connections, right? Easy to understand that what is the remedy there. In terms of joint panel zones, web compression buckling, opposite beam compression flange can happen, web shear buckling can happen, and fracture at weld in case of doubler plate connection. We will take up this panel zone in a separate set of slides where I'll give you what the current code is giving. But if such kind of failure is happening, yes, we have to give the requirement as per minimum shear strength requirement. We have to give to the panel zone. We have to provide stiffener plates as a continuity plate or doubler plate requirement has to be given, as I mentioned. Doubler plate is to increase the buckling capacity of the panel zone. The stiffener plate, which is the continuity plate, is to give stiffening to the column flange in order that they do not undergo local buckling. And then controlling welding details, do not give higher heat input, because if you give higher heat input, it may reduce the yield strength, it may produce residual stresses in the members, etc. Columns, yes, local buckling can happen by meaning lateral torsional buckling, which you have heard, would have heard in a beam. In terms of this thing, it is torsional buckling to be precise. And then global buckling can happen. The remedy is to give adequate axial strength, adequate compactness ratio, and lateral bracing has to be provided, as in the case of a beam, right? Column splices, same as beam and column connection, and column bases, many things can happen: anchorage, stretching or pull out, fracture in the base plate, fracture in column to base plate connection, and local and lateral torsion buckling at plastic hinge. The remedy is column bases could be designed to gusset plate or the base plate design. We have to do it perfectly. Now, I don't know whether you can interact with me with or not, like maybe access might not be there. So I'll ask this question to you. In terms of response reduction factor for SMRF is more than OMRF, will it translate into low cost building? You understand that the response reduction factor for an SMRF would be very high than an OMRF. SMRF के लिए 5 है, OMRF के लिए 3 है. तो will it translate into a low cost building or not? Right? You may say yes, no, maybe, but the answer is, in a moment resisting frame, normally the design is governed by the drift criteria, right? More than the strength criteria, it is a drift, because stiffness is very low. You have beams and columns which is providing this lateral stiffness to the member, and in comparison to a brace frame, you know that if you give braces in a diagonal fashion or in a X fashion, it is going to increase the stiffness of the structure. But you can understand that for an SMRF or an OMRF, drift would be the governing criteria in terms of your final design. So changing from SMRF to OMRF is zyada important. The more important criteria would be the drift criteria, right? With respect to design, what are the factors that may affect, which means apart from the strength criteria? So you may be using IS 800 or 1893 load combinations, like dead load plus live load plus earthquake load, where in most cases 1.5 dead load plus 1.5 live load plus 1.5 earthquake load might be governing your strength criteria. But as I mentioned, for a moment frame, it is the drift criteria that governs. Other than that, क्योंकि drift ज़्यादा है, since the drift is higher, P delta instability or the second order effects might be there. Strong column, weak beam criteria. Even if you have designed your beams and columns as per the demands that have come, the final section size selection would be based upon the strong column, weak beam criteria. So your section sizes are getting bumped up. I mean, it gets increased. Then compactness limit. So if it is in a high seismic region, now you understand that you have to give a plastic section. So again, your section sizes are going to increase to satisfy the compactness limit that is given in table 2 of IS 18168. And then available sections. So what we have a problem in India is we have a certain code, like you must have heard about SP6, which gives the details, available sections for, let's say, angle sections, eye sections, channel sections, etc. So with respect to that, you have limited amount of sections. So you might have always faced this issue that whenever there is a requirement for a beam and you check your section modulus requirement is so and so mm cube, and you want to select a section which is nearby to that, there is a big gap between what you want and what you have, right? So that also adds up to your overall strength of the member that you're going to give. So if you do a pushover analysis, let's say you do a steel building design and you do a similar RCC building design, the kind of overstrength that you get from an RCC structure might be of the order of 2.5, whereas the kind of overstrength that you get from a steel structure might be from the range of 3 to 10. It can go. Where the 3 to 10 comes in is that, okay, when you do a pushover analysis, yes, or a time history analysis, you are going to give the expected strength of the steel, correct? Which would include the uncertainty factor that we talked about earlier. It would also include the strain hardening effect that would come in a steel structure. So increase in strength is coming from there. Apart from strength criteria, your drift limits is going to bump up your size of beams and column sections. Your strong column weak beam criteria, compactness criteria, section availability is also going to push you to use a higher section as per the codal requirement. So which will increase your lateral strength of the member or the structural system to a very high value, right? So certain solutions, which is not a complete solution, as in the case it is going to remove it, but you can use deep flange sections for columns if it is available. But the limitation is that architecturally it would be an obstruction, right? Limiting bay width, what is a range that you go for? Think of what is a range of the beam span that you can go in a steel structure versus an RCC structure. So in an RCC structure, maybe you would need columns like, okay, 4 meter or 3 meter to 8 meter takka span is like efficient span where you use an RCC structure. Whereas in a steel structure, you can go up to 6 to 12 meters also you can go, which means if your material consumption is getting increased, you can increase the bay width size and kind of reduce the section sizes, or increase more space in it. Reduce the section sizes is not possible, but reduce the number of column section that you are going to use, so that at least what you lose in terms of material consumption, you can gain in terms of the functionality or the larger space that is there. A few things, what do you say, tips is that lighter, shallower section and their connection that meet code compactness requirement tend to have a larger inelastic deformation capacity than do deep, heavy sections. So try to control your bay width in such a way that you don't end up with a deep section, rather than it is good to go for a shallower section. And desirable to distribute lateral resistance in SMRF system to multiple bays rather than to very less number of bays. So what is the practice in America is, you have a moment frame in which you have sections, you can have multiple frames like in an RCC to be a moment resisting frame. But what they do is they do only design the SMRF as the most peripheral moment frames, and rest of the interior frames are only gravity resisting moment frames, which are made compatible. I mean, deformation compatibility is checked, but the onus of taking the lateral forces is given only to the peripheral frames. So that way they don't utilize the interior frames as moment frames, and reduces the redundancy of the system. The advantage that they have by using only the peripheral frames, you can understand the demands on the beams and columns will be higher. Their section size demands would be very higher, but they have adequate sections with different thickness ranges, and different depth of the section is also available, that they are okay to go with such kind of an arrangement. Since we don't have the luxury of too many sections available with us, it is better for us to even go for using all the frames in a particular direction to be moment frames, which reduces your section sizes, which also which also gives you redundancy in the system also, right? Now, the next thing what I want to talk about is, I already told you that in terms of a moment frame, it is the drift criteria which governs the overall performance of the system. Now, drift has two components. That one is a shear drift, which is caused by the flexural and shear deformations in beams and columns, and the flexural drift that is there, which is caused due to the axial deformation of the column. So if you have a slender, let's say frame or a slender structure like this, where the drift is governed mainly by the axial deformations in the column, and if you do an analysis and you find that your drift is going beyond limit, then rather than playing with the size of the beams in order to reduce the drift size. Playing with the size of the columns would help you to counter the drift problem quicker, faster than aiming for the beam section, right? But if your structure is little bit stout, low rise, where shear deformation is or shear drift is going to be more predominant, there rather than attacking the columns in terms of increasing the column size, moving from the beam size, changing the beam size would be a better option. Because what I want to say is if flexural drift is confirming, if you keep on changing your beam size, obviously it will have some effect on the overall drift performance, but that will indirectly cause you to increase your column size just to conform with strong column, weak beam. So ideally what should be done, the big takeaway from this slide is what should be done if your drift criteria is getting exceeded. For a particular building, what to do, and for another type, shear drift type, what to do. That is the whole thing that I wanted to explain here, right? That is what is written here also, that if strong column weak beam criteria has to be satisfied. So if I am targeting, so earlier in the particular slide, we have given that what is the ideal performance from a moment resisting frame, where we mentioned that, okay, I need plastic hinges or the yielding to happen in the beam ends, and I am happy with having it at the end of the columns also. So to achieve a most ductile behavior while designing, what all you need to think about is level of compactness required of beams and column members has to be adequate, which is stable too. Frame members must be laterally braced for stability. Frame members means beams and columns should be laterally braced, right? Implementing strong column weak beam design philosophy, fine. We'll look at further slides will be on how to achieve that particular criteria. Then special requirements are associated with demand critical welds. Like what are demand critical welds are? The connections or the beams where plastic hinges are getting formed, which will have higher deformations and nonlinear concentration of nonlinear hinges and nonlinear yielding to be more. The weld of that beam to column will be what would be called as a demand critical welds, because it will have the highest demand to accommodate the beam rotation. The nonlinear performance of the beam has to be all accommodated by that particular connection. That is why those connections will be called as demand critical welds. And then the next name is designated protected zone. So if you have a moment frame, you know that this particular location at the beam end and the other end is going to go into nonlinearity. So that particular location, a certain length over which code gives you a value of how much that particular length of plastic hinge is going to be. So that particular location is what is called as a protected zone. So we have a protected zone and the associated demand critical welds. And the protected zone is the zone where the beam or any member is going to undergo nonlinear hinges or nonlinear performance, and you don't want any kind of cutout or any kind of connections, any member coming, any secondary member or any non-structural element getting welded to that particular location, because any damage to that location might hinder your overall nonlinear energy dissipation capacity of the member, which will jeopardize your structure. So you have two additional terms, new additional terms that you are hearing about, what is demand critical welds and the protected zones, right? The next comes shear yielding of panel zones is a very ductile behavior. Now that is very interesting in steel structures. In RCC, we would have heard that shear performance is kind of very brittle. You should not, go for any kind of shear kind of behavior. But if you look at the behavior of a plate, if you just look at textbooks and everything, with respect to a shear behavior of a plate or a plate undergoing pure shear, as to how it behaves, when it yields, when it buckles, the kind of energy it dissipates, you will come to know that it is a very ductile behavior. It is a high energy dissipation kind of a behavior. So you have to think that if you want your panel zone where your shear forces are high or where your shear forces dominates, what kind of a behavior do you want? Do you want it to behave elastically? Do you want it to behave inelastically? You have to decide based on how you want to. We'll discuss panel zones separately, and then you'll get more information as what to happen. And then inelastic behavior of beam column connection is obtained when limited yielding occurs in the panel zone simultaneously with plastic hinge region. So what is being mentioned here is through experiments and literature, what we have come to understand is that if you have the panel zone yielding, very limited yielding is happening in the panel zone along with the yielding of the beam member, that particular combined behavior is better for the performance of the overall moment resisting frame, right? It gives you the maximum energy dissipation. So if you have the beam alone acting as your energy dissipation element, the maximum onus will be on beam and it will fail early. But if you have a helper in terms of the panel zone also undergoing limited yielding, it increases the lifespan of the beam in order to dissipate more energy, right? So for doubler plate, you may need doubler plate or continuity plate accordingly. Now this is where one particular thing I want to show you is that you can see the I section, the representation of the I section that I have shown here. So you can see that majority of the I sections are oriented in this direction. You can see the H in this direction. This is also this, and this all is in the X direction. So I can use moment frames like from here to here. This particular, if I can orient this way here, everything I can use. But in this direction, in the Y direction, you can see that I have less amount of moment frame that I can achieve. So if my, let's say, kindly watch this particular location closely, where I have a beam which is attached, the major axis of the beam is providing moment along the major axis of the column, and this particular column. But here the beam is applying moment about the minor axis of the column, right? So when you say a moment frame is there, ideally when we say moment frame, okay, a beam getting connected to a column is a moment frame. If you use ETABS or STAD, you just give a frame element, a beam and a column, automatically it considers complete rigid joint between them. But what you have to understand that if you have the major axis of the column, the beam is applying the moment about the major axis of the column, then the rigid kind of, the width, about that width, you can give a rigid connection. You can give a proper connection here, which can be rigid and which is able to transmit the total moment capacity of the beam to the column. But regarding here, you know that the outer plane stiffness of this I section is weaker along its minor axis. So if my beam is applying moment about the minor axis of the column, whatever may be the connection, if I directly weld my beam to the column, it will not be a purely rigid connection, and it will not be able to transmit the total plastic moment capacity to the column, which means it will not be a proper moment frame of the system. So you can understand that in a PB structure, let's say your columns are always oriented along a particular direction. So that particular direction, you can call it as a moment frame. But what about the rest of the span in the Y direction? The problem there comes is that you cannot give a rigid connection between the columns. So that cannot be a moment frame. So you might have to opt for a different lateral force resisting system in Y direction. So your response reduction factor in X will be for a moment frame, and Y direction it will be for another system, maybe an EBF or maybe for a CBF system. If you are using a box section, yes, the problem gets sorted out because then there is no problem. But if you are using an I section, always remember that if your beam is applying moment about the major axis of the column, that particular section is good enough to carry all the moment. So a rigid connection can be properly given. All the connection in AIC 358 I to I section that is given there are from this major to major axis kind of a transfer. Whereas you will find literature as to people, researchers trying to find out a particular connection for outer plane action of the column where the major axis of the beam is applying the moment to the column, but it is not completely a thorough procedure. There is no pre-qualified connection for a rigid connection in that case. So whenever you model in ETABS or model in STAT, try to give a release, a moment release at locations like these, because you will not be able to transfer the total moment there. So there is no point in assuming it as a rigid connection and designing it or assessing the performance further from there. I hope it is clear. This is very important. And majority of the times when practitioners do this, I find that they don't see this particular fact that this performance can be different. So with respect to IS 800 2007, this is the old way of defining a special moment frame as to how it should be. So it says special moment frame should be made with E250B, should be shown to withstand inelastic deformation corresponding to a joint rotation of 0.04 radians without any degradation in strength and stiffness below. So it is telling certain strength has to be achieved, but the rotation, the connection or the beam joint has to achieve should be 0.04 radians, which is similar to 4% interstory drift, but without any degradation that is happening in the overall. I mean, there should not be any drop in the hysteresis curve or backbone curve of the system. Now, if you look at the new code IS 18168, which is for high seismic region, if you read it carefully, why I have given it, why I am reading this particular code is with you is because of a particular reason. You can see here, special moment resisting frame designed according with these provisions are expected to provide significant inelastic deformation capacity through flexural yielding of the beam, limited yielding of the panel zones. It says it is okay to have limited yielding in the panel zone, little or no yielding of the columns except at the base. So it is defining a boundary that, okay, you are my deformation controlled element and you are my force controlled element, the column being the force controlled element. Special moment frames may be used in any seismic region except for buildings taller than 15 meters in seismic zone 4 and 5, which I talked to in the beginning, because beyond 15 meters, the drift criteria solidly kind of governs your total design, and it kind of does not give the enough energy dissipation. So leave it out in terms of heights more than 15 meters. And yielding of beam of column connection and SMRF shall not be permitted. The connections should remain always elastic, which is understandable by that fact. So if I give a list of hierarchy in terms of what should be the most strongest member in the beam moment frame, the strongest should be the connections, then it should be the columns, then comes the panel zone, and then comes the beams. So the weakest are the beams. I go in the opposite order. The weakest should be the beams, then panel zone, then column, and then the connection. Right? In terms of ductility, it is just the opposite. I want maximum ductility in my beams, then panel zone, then connection, and then the least amount of ductility I want from my connections, because I don't want any nonlinearity to come. So I want it to be almost elastic. Right? The next one, this particular clause, I want to read it clearly because it is the most important clause here, which many of the practitioners might be missing around. It says, beams in SMRF are permitted to carry gravity loads through composite action with reinforced concrete slab. For lateral load action, composite action should not be considered. This is the most important line. Why it says so? You understand that in a steel building, you have a deck sheet. The deck sheet is connected to the beam through shear studs, and the concrete is poured inside that deck sheet to for the flooring. Now, if I have a shear stud, the beam and the deck sheet connected with the concrete being poured, I can use the composite action to design the beams. Right? You can agree that if I design the beams, and I can take the equivalent beam with the slab also considered, and I can design it accordingly. Why the code says lateral load action, composite action shall not be considered? It says don't give any shear studs in the location where the plastic hinges are going to get formed. Which means if you have a rigid beam column connection or a moment frame in your particular building, you can give shear studs along the mid length of the beam. You can give a 3/4 length and everywhere. But if you feel that that particular beam has a tendency or can form plastic hinges at the ends of the beams, then for the length of the plastic hinge location, which is given as, I think, twice the depth of the beam, it gives here, further abrupt changes in beam flanges through actions like drilling holes or trimming of flange width and use of shear studs are provided in the beam end regions of length at least twice the depth of the beam. So the code gives the plastic hinge region is twice the depth of the beam. In that particular region, don't give any shear stud so that composite action will come into play. So what it means is that, okay, at that particular location, when the beam undergoes nonlinearity, let's say it undergoes cyclic load where you can have tension at the top as well as tension at the bottom, you don't want the composite action, because then the hysteresis curve becomes asymmetric. On one side, if you consider shear studs and the concrete action, the compression phase becomes more stronger than the weaker tension side. If you have an asymmetric hysteresis curve, you will find that the premature failure of the section happens very quickly. Right? So for that instance only, the code says, okay, you want a symmetric action, you want plastic hinging to form only in the beam. So don't consider any kind of shear studs to form there, which means no need for considering any composite action at that location, which means you don't have to consider strong column weak beam with the composite action of slab being considered at that location. Right? I hope in RCC, where you have no such kind of provision there, when you consider strong column weak beam, you have to consider the composite action of the slab. Otherwise, you end up with a strong beam weak column kind of concept. So that kind of a problem is not there for steel structures. The next is, you can read through, this is like column connection ke liye, shall be capable of accommodating story drift of 0.04 radians without loss of strength exceeding 15% of the beam plastic movement capacity. So it doesn't say there should not be any even 1% loss. It says okay, 15% loss is okay. Now the protected zone, as I said earlier, that 2D zone which came in the last clause that we read, the region where the plastic hinges can form, the region at the end of the beam equal to twice the depth of the beam subjected to inelastic straining shall be designated as protected zone. Steel headed stud anchors and other fabrication and erection attachments shall not be placed on the beam flanges within the protected zone. Right. Then beam section. Now, this is another important aspect. This is another clause that you have to understand that earlier in SP6, you had tapered I sections and everything available to you. ISMB 600, ISMB 400, ISWB sections are all tapered flange sections wherein your flange would be tapering towards the end of the flange tip, right? So now in this particular code, it clearly mentions that only doubly symmetric parallel flange standard rolled section as per the IS 808 or built up section would be used. So it does not allow you to use tapered section, only parallel flange sections needs to be used. So where do you look for the IS 808 ke alawa 12778 is the equivalent SP6 for parallel flange sections. You can get your section size from that particular. So for beams and columns, you have to use parallel flange sections in totality. Now, clause 6.3 with respect to moment frame is not about lateral bracing, but it is with respect to horizontal bracing that I talked about earlier, which you give underneath the slab to support your, give lateral support to your beam in order to avoid any lateral torsional buckling or your columns such that the effective length is getting reduced. This is that bracing requirement. So it says, okay, it has to be lateral bracing shall be attached. Look at C here. The lateral bracing shall be attached at near or both flanges near the point of inflection in the beams bending in double curvature. So what it means is that I'll come to beam splice later. You can see a particular I section here, right, which is being subjected to moments, equal moments at both ends. If I plot the bending moment diagram with respect to this, I'll get this particular profile. But if I plot the deformation diagram, you can see the pink color is the original undeformed shape. Whereas by providing this, you can see along with the deformation with respect to the moment, there is a twist. You can see this particular area is getting highlighted at this location. There is a twist that happens, right? So due to lateral load or due to gravity load, there can be a condition wherein you can have your beam undergoing a particular twist, wherein if you give only a lateral support to the middle of the beam section, that is not enough. It will still rotate. So if I give a support, what you can see as a red color arrow here is a lateral support given at the CG of the I section, but that didn't avoid the rotation of the blue color is still happening. But if you provide lateral support to the top and bottom flanges of the sections by any means, then it will avoid the rotation of the section. So this is the whole idea of giving horizontal bracing to the member. Just by giving any section to the CG of the I section will not do. You have to understand the mechanics behind how it is rotating and then what to restrain. So you can see certain images here with respect to how the primary beam has been restrained. So here you can see a small beam here. This is the primary beam. And then to avoid rotation, what a separate element is given here with a plate attached to the bottom flange as well as for top flange. This is an image of that particular element. So this is a primary moment frame. This may be a secondary beam. You have something welded at the bottom flange coming here, and then here is a total plate here. So this is being, stiffened by an additional beam. Say reaction like stiffened kiya jata hai, but this is the fact that I was telling. So if you have to restrain a particular beam against lateral torsion, then you have to kind of give at the appropriate location as per the deformed shape of the member. That is what this particular bracing thing talks about. Now, with respect to splices, you understand that okay, when we buy a beam section, a built-up plate. If you buy a plate for a built-up section or a rolled steel section, it does not come in infinite length. Either it comes in 6-meter length or a 12-meter length as per the manufacturer's production line. And so, where should we provide a splice is what is given here. So, if you are giving a splice in a beam section, it should be located at least 3 dB from the face of the column or dB from the line of action of any concentrated force. So just to give you an idea as to splice के लिए भी इसमें definition दिया हुआ है, उसके लिए मैंने ये लगाया हुआ है. Now you can see for column, you can read here that column splices shall be located in the middle third height of the column, at least 1 meter away from the beam to column moment connection. What you see here is a real kind of construction which is done. This is a fabrication drawing, which project I will not mention, but you can understand that the splice here, if I tell you point out the mistake here, you'll find out that, okay, there is a mistake right around here with respect to the column splice. Let's not talk about beam splice right now. This is the column splice here, and you can see the depth below the beam is only 230. The intention of the architect or the designer, due to the pressure from the architect, was that he does not want to see such kind of a splice at a location which is intermediate to the floor. So he wants to hide this particular splice connection inside the false ceiling. So such kind of a demand, when you look at in terms of what the code wants, I mean, you understand that why the code says between middle third, right? You can understand why the code says middle third. The only thing is you have to plot the bending moment diagram in a column when considering lateral loads and gravity loads, and you will understand why it says middle third is the more prominent location. And it also gives you how much strength it has to be designed for. So such mistakes needs to be avoided. As an engineer, as a designer, if you are going for a performance-based design, before you do the performance-based design, to get to the correct kind of a behavior, you have to design it properly, right? Now, the next thing is an important clause which you have to understand, that earlier our strong column weak beam ratio for steel in IS 800, the right side one is as per IS 800, was given as 1.2 as the ratio. Whereas this is a new code which gives 1.4 as the ratio that has to be achieved, right? You have to understand one thing is that here the definition is quite simple. It says sum of the moment capacity in the column above and below the beam center line, and MPB is sum of the moment capacities in the beam at the intersection of the beam and column center line. Very simple. People would be doing Fi into Zp, Fi into Zp for the column, Fi into Zp for the beam, done and dusted. If you are using ETABS kind of a software, the ETABS software was a little bit more kind of thoughtful or savior of you, and it was taking some cue from the other codes, international codes, and it was taking that, okay, if an axial load comes in a column, should we consider that something for that also? So it was inadvertently doing certain extra things for you other than what you were doing. If you're designing strong column weak beam as per this particular clause using an Excel sheet, you might have made a mistake, right? The new code, what it does is, it says, okay, if you want me to find out the strong column weak beam ratio, let me make the column the weakest and let me make the beam the strongest. I mean, let me assess the strength of the beam in the highest possible way, and let me assess the column strength in a lower way. So you can see Fi into Zp is your normal, what we say in terms of Fi into Z that we do. 1 minus Pu by Pd is to consider the effect of axial load effect on the column. So higher axial load, lower axial load, what will happen to the column capacity is getting considered here. If you look at the bottom particular fact, you can say, okay, Fi into Zp is the maximum, what do you say, the moment capacity of the beam that we would have already calculated. But you can see the uncertainty factor coming here, Ry. And then this is to consider the strain hardening effect. The 1.1 is to come as the strain hardening effect. The strain hardening effect also occurs in columns also. But what I said earlier, make the column, whatever strength of the beam to be the highest, and make the column strength to be the lowest. So we are not considering similar factors above. We are considering strain hardening, uncertainty factor, everything for the beam, but we are not doing the same for the column. And then we are finding out the ratio and ensuring that it is 1.4, greater than 1.4. Now, two things to be gathered from here is, there is too many uncertainties in terms of when we say we don't want to give shear stress, etc., that composite action doesn't come into play. There is a thing that, okay, rest of the slab is not going to go anywhere when the beam is kind of deforming. It may have a small play in terms of the strong column weak beam or the deformation of the beam that is going to come. And there are other factors also which we might be ignoring while the final structure comes in. Let's say infill panels, what is the effect of there on this particular aspect, etc. Nothing comes into picture. So by giving this kind of formula, we are ensuring that, okay, worst case scenarios, are we tackling or are we countering? So 1.4 seems to be a higher value for you, but trust me, when you do these tests, it may come on a lower side unless you have a total control. So if you look at the same formula in AIC 34116, there this comes up to be greater than just 1, where they have greater control over their material, their execution, etc. So let's say 1.4 is out of fear that we have kept it as such as a higher value. Here you have to understand the second point that I want to make you understand is, whoever has designed a particular steel building earlier, or students, if you go and visit a particular steel structures in your future endeavor or something, kindly look at if they have used this particular criteria. Obviously, the ratio of this thing, if you consider axial load, if you consider Ry, if you consider Zp, in reality, if you consider the exact values of the strength of the material, the ratio might be in the opposite direction as to make it as a strong beam, weak column kind of a concept. So there may be many steel structures out there, many, for which retrofitting would have to be done in terms of it has to be improved, or its design has to be some kind of retrofitting has to be done in that particular case. But for rest of you are designing a new building, this has to be countered, right? Now here I have kept a question just to cut the monotony, just to relax you a bit as to what should be the, I mean, if I increase my grade of steel today, if it is 250, tomorrow if I increase to 450, would it do any good, right? So the answer is, if I increase the grade from E250 to E450, you might say that, okay, my section size will get reduced. But if my section size gets reduced, then there are many other problems that may also come along with it. It may be drift may increase, the fatigue strength may decrease. So it is not a direct relation ki, okay, by 250 to 450, yes, it will reduce your section size, yet yes, it will reduce the consumption of steel, the cost of your building may come down. But sometimes when the drift is the criteria that is going to govern your structure, maybe grade of steel does not matter. If fatigue, like in a bridge, if fatigue is the criteria, you have to check which elements are going to help you, and if that particular thing is not governing, if the strength is governing, then well and well, you can go ahead with this. Now here I am keeping a certain image. This is a moment frame only. You can see the welding that has happened. I mean, it's not visible clearly, but yes, this is a moment connection, continuity plate, everything is given. This particular type of moment frame connection is known as a reduced beam section. Now, in terms of what we have seen with respect to the image of where the plastic hinge is formed, or the code says 2D distance over which the plastic hinge gets formed, there is a challenge that how can we kind of ensure that it forms at a particular location, that it does not form near the connection regions, as that it forms any kink or failure of the connection. If you want to avoid that, you have to ensure that it forms at a particular location where the plastic hinges get formed. So reduced beam section is also a type of moment frame wherein the flanges are cut in such a shape that yes, it can take the gravity load demands that are there, but during an earthquake, due to this particular reduce, I mean, you are creating a weakness at this particular location, that plastic hinges get concentrated there, relieving your connection zones from very high demands. If the plastic hinge would have formed at the face of the column, then the demand in the welds would have been much higher. But if you ensure that it happens here, then well and good, the performance is much better, right? Now, coming to this handbook, you would have seen, right? SP6 1964, you would have had an idea wherein you get the section size for ISMB rolled carbon steel sections of channel sections, angles, I sections, etc. I don't know how many of you know about this particular code, IS 12778, which is the code which will give you the section sizes to be used as per IS 18168, which is that parallel flange sections. Now, any day, if your section, if you're connecting, I mean, normally what you do, you bolt in your flanges and etc. If you're doing connections in the flanges, etc., parallel flange behavior is much better than a tapered flange, obviously to the reason that the cross section is decreasing. I mean, if you look at SP6, if you open, the thickness of the flange is actually not located, not at the tip, not at the joint of the web area. It is some average locations in between. But when you look at this particular parallel flange code, if it is T is of 12 mm, it is uniformly 12 mm. So whatever calculation that you do for edge distance or shear failure or bolt block shear failure or any net section failure, the thickness what you would use in a calculation would be exactly the value. So in that way, parallel flange sections are much better than tapered sections. Now, if the question comes in as to what is the maximum depth of rolled dissections that are available in India, if I ask you, if your answer is 600 mm, then you're wrong. The maximum section is 900 mm, right? Which is as per this 12778. If you go, this particular code, if you see, this has come up in 2004 itself. Many don't know. I mean, I'm assuming that some of you know and some of you may not know. This code has long been there with respect to parallel flange sections, and the maximum section available is 900 mm. But if you go as per IS 800 2007, which is a more relaxed kind of a code in terms of classifying the section capacity, Number of sections in SP6 was 65. This is only I sections that I'm mentioning. And 12778, you have a larger pool of parallel flange I sections that are available there. But the number of sections, plastic sections, जो इसके category, मतलब as per table 2 of IS 800, जो what whoever classifies is only 28. And as per this is 132. So anyone using ISP6 earlier on, if they designed a particular section, found out a section modulus for a beam, would have had to have used a higher section just in order to satisfy the design, because none of the sections would have classified as plastic section. They don't have enough pool on the right side to get selected. Same goes for this particular thing, right? You have a larger pool right now from 132 sections, but how many are enough? Once you design only, then you'll be able to understand. This is a chart wherein I have kept Indian sections versus American sections which are available for construction. And you can see that if I look at only the 400 depth, which is depth of the, let's say, beam, total depth of the beam, you see this section modulus availability for the 400 to 500 depth, how much the amount of section modulus available if I use for American section, and how low our section modulus are. Which means the same problem once again is that I may not have enough sections to design my steel moment resisting frame, where I'll have to go for even higher depth sections to achieve my section modulus. And one more thing is that since they have a lot many sections in this 400 range, what their architects do is they don't have to worry about the structural engineer being able to find out a section of a particular size. What they do is they make a box of 450 by 450. At the location of columns, they just place that column box of 450 by 450. They know that this particular gentleman, the structural engineer, would find enough sections in that particular depth such that he doesn't have to worry about tomorrow. In India, we normally go to an architect and say, sir, 600 is not working. I need a higher column of 800 or 1 meter. Architect says, no, it hinders with my architectural plans. Then you go for built up sections, etc. Right? So that kind of a problem is avoided if we have enough sections also in our design. Okay? So this you can go through. This I have once Tajul shares the slides with you. This is like how to go with respect to the beam design. The beams to conform to compactness criteria. I mean, what all criteria should be thought about for the design of beams? I've included it here. For column designs, what all? It's like compactness criteria uh, 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 with respect to what should be achieved. Then lateral bracing should be provided. That kind of a criteria is what is given here regarding splice also. Now here is the main sorry, here is the main thing that we want to talk about. So we know already, I mean, you might have already got the experience with respect to designing of a beam. You might have got already the designing of a column in your undergrads or your master's program. But panel zone is a very tricky thing. Now you can understand that you have a beam on the left, right here, and a column there, and a column at the bottom. Now, if I look at the at a particular joint in a particular frame, you can understand that this is a bending moment diagram variation, and I have a huge spike in the shear force at that particular region. So it is the rate of change of moment that happens in that small area, that small panel zone, which might be a very small width of, let's say, 300 by 400 or 500. The shear force are so high that the shear behavior dominates in terms of a panel zone. So the element, the shear panel zone, is governed by the yielding in shear. And if not, if it is very thin, if the panel zone is very thin without any doubler plate, it may undergo shear buckling. I mean, buckling due to shear forces. That is shear buckling that I mentioned. So that is why people give, they check the thickness of the panel zone. If it is not adequate, they give doubler plate, etc. in terms of increasing the shear buckling capacity. So earlier, I mean, if you take the chance of US, what they used to do was earlier they used to design it as to achieve strong column BP. So they would want their panel zone to be entirely elastic throughout the behavior of the moment frame, whether the beam is undergoing nonlinear plasticity or anything. They didn't want their panel zone to go into the elastic region. But later on, this is like 1980s, it happened that, okay, they wanted the elastic behavior. And in 1988, around, Crowinkler actually came up with the nonlinear kind of a behavior, that they understood that, okay, the panel zone has a ductile behavior in shear. they can depend upon it in terms of yielding and energy dissipation, that you have two elements working synchronously in terms of reducing each other's burden. Like if beam was alone dissipating energy, it would fail earlier. So if I have the panel zone also yielding along with the beam, a limited yielding if it is there, then it shares the energy dissipation and it relieves some kind of pressure from the beam. It's like a combined kind of an effect in terms of resisting a particular force. So they found that it was good if we could achieve. So they understood, and that stands still today, that if I have panel zone yielding and beam yielding being the event that has to occur first, panel zone being the second one. I mean, there should be a hierarchy between the two. If that happens, then the frame dissipates enough energy without any kind of what do you say, nonlinear deformation exceeding any limit, etc. It has adequate rotational capacity. Everything works well fine for it. But what happened during 1994 Northridge earthquake after that particular event? So I said 1980, they were going as per strong column weak beam. The panel zone was elastic. 1988, Crow-Winkler found out the nonlinear. I'll show you the graph that he thought was the best way it could be achieved. Like you go tap into the benefit of going into the nonlinear property of panel zone. And then 1994 Northridge earthquake happens, and they find out that if I use the 1988 kind of a theory where I depend upon the nonlinear hinging, and if I don't control the nonlinear behavior of the panel zone, the connections are getting failed due to kinking at these corners. So if the panel zone is kind of deforming too much, the connections at this location, and this particular area will be stressed more, and those were able to, I mean, those were undergoing failure. So such kind of failure prompted them again to go back to the original proposition, which is like this particular. I mean, if you look at their code, AIC 360, I mean, they have two codes, that is IS 800 ka equivalent unka 360 hai, and for 341 18168 equivalent is their 341, right? So if you look at AIC 360 for design of panel zone, you will find a similar formula, which is, this is depth of the column, thickness of the web of the column, which is the panel zone, this thing, Fy multiplied by 0.6 they have. But here 0.55 I can explain you is that if the plate undergoes pure shear, as per von Mises criteria, we mentioned that the yield is Fy by √3, right? And then they take 0.95 of this depth of the column. So which means you're not taking the whole depth of the column to leave out the flange thickness, etc. They take 0.95 as the factor. So 0.95 divided by √3 is what comes around to be 0.56, 0.57. So that is the whole this thing. So this is like, okay, this is the point where we think that the yielding of the member will undergo. I mean, if I have to consider the yield strength of the panel zone, this is the equation that they used to do. Crow-Winkler thought this might be a better way to understand this particular thing, as to have a limited yielding in this thing, where they went into this particular formula, where apart from what they found is, once it yielded, it had additional capacity. Now, where this additional capacity was coming from was the plastic hinging in the column flanges at these four locations. If you look at Eurocode, you might be able to understand that equations much better. Both are the same thing. This is as per AIC 360. This is as per Eurocode. You can understand 4 MPL. 4 MPL is the plastic hinging occurring in the column flanges at these four corners. That is increasing the capacity after the yielding in the panel zone has happened. So they wanted to tap into this particular kind of criteria. But later on, as I said, after this is 1988. After that, when the real code came in, that is after that 1994 Northridge earthquake came in, and they found out that this was not enough in order to control. So our code, where does it stand right now is, if you remember what RY, FY, ZPB was there, you can think it is telling us, 18168 is telling us how to calculate the panel zone demand. That is finding out the bending moment at the face of the column. That is Fy into Zp is the what do you say, the flexural capacity, plastic moment capacity of the beam, including the uncertainty factor, including the strain hardening factor, as this is the peak value that the beam might transfer. This is 0.95 dB to find out, it's like moment divided by the lever arm, to find out what is the shear demand at the face of the column near the panel zone. And how do you find out the panel zone capacity? It gives this particular formula with the partial safety factor of 1.1 given there. Rest, the idea remains the same. 0.95 divided by root 3 comes up to 0.56 or something. In American code, it's 0.6. Rest, whatever is there in 18168 is these two clauses. One is to avoid the buckling. It's a check of shear buckling. There should be a certain thickness of the panel zone. If the thickness is not enough, provide doubler plate. And this is the requirement for the continuity plate to avoid the local buckling of the flanges of the column. So if you look at these four formulas and look at what the Euro code and American code are currently giving, even American code, if you look at, if the axial load ratio is less, they use this particular formula with a 0.6 here. If the axial ratio is more, they use this particular formula. So they still are not left out. So in this particular case, where Indian researchers can also look at it, is the world is also confused on this particular matter. One thing that is certain is, yes, panel zone yielding along with beam yielding, with the beam yielding initiating first, is the most ideal behavior of energy dissipation. But how much amount of yielding? Everyone says with the word limited yielding of panel zone is enough, but nobody quantifies as to how to limit that particular value. Even our code currently does not talk about that extra strength, because my strength of the panel zone can go beyond this. But it does not say, it keeps it as it is, means with the strong column, weak beam and everything coming into picture, maybe what we are, maybe I'm using the term maybe, that we are doing a strict design of elastic panel zone design, rather than if you remember the first clause that I read in our 18168 is, our intention is to have yielding in the beams and limited yielding in the panel zone, but the intention and the clauses does not match. So as an Indian researcher or Indian designer, you can go ahead with this particular. This is much better in terms of, rather than depending upon the extra strength of the material, pushing the panel zone into more non-linearity, and then having no control over how to control the kink or the failure of the fracture. This method is still fine. But yes, the beam will be overstressed in this particular case. How much so has to be assessed by academicians and researchers, right? Sorry. Any problem with this particular thing? You can see this is a reduced beam section. And what is the problem is, if this is a reduced beam section, it is the web is welded here, the flange is welded. So this is a rigid moment connection. This is a column. So the problem here is, in the protected zone, this connection has been provided, which is a strict no, right? So you have to understand one by one as to what we were explaining till now. The next is, you can see this is an end plate connection, rigid connection that is there, I section that is there. The I section is oriented in the major axis in this particular, like the beam is applying moment in this major axis. So this person has used a moment rigid connection in this direction, that is absolutely fine. Whereas along the minor axis, correctly he has used a shear connection. So the flanges are not getting connected here, are not connected here, only the web is connected. So he has done a good job in terms of understanding what connection, how much I can yield from the joint area, as to who can be my rigid connection and who can be my flexible joint area, right? This is a column splice joint. CJP welding in India, it is very difficult to do with a proper welder and the control that it has to be done. If it is done correctly, absolutely well and fine. The one thing is, it is very close to the flooring area, so it is not known. I mean, one can see that, okay, I'm not sure if it is in the middle third or more than 1 meter as the code says. So now you have to follow these kind of guidelines in order to ensure that the detail has to be given in the middle third or above 1 meter of that particular what do you say, the joint area. Now here is one more problem with our Indian code, where I would want everyone to have a notice. As I said, AIC 358 is a code that Americans have developed in terms of pre-qualified connections. In Indian code, annexure F, we have a classification that is given, a drawing per se, in terms of what is classified as a simple connection and what is considered as a rigid connection. But we don't have a procedure, set procedure for, let's say, if I want to join E250 to 250, if I have to join E350 to 350 or any other kind of connection, I don't have a proper procedure in hand in terms of doing the connection. The only thing I have is how to classify a connection has been given to me. So if you look at this particular clause in F4.3, which is based on this particular diagram, you can see that the clause here is relating rigid connection as mu by mpb, m dash m1 is equal to mu by mpb, where mpb is the plastic moment capacity of the beam section. So whatever the moment is getting transferred by the total moment capacity of the plastic section, if it is more than 70% in terms of strength, it is be called as a rigid connection. But it cannot be alone called as a rigid connection unless the stiffness also matches. So you can see in this particular, if my curve, if I start from here for a rigid connection, the moment rotation curve unnormalized, this is normalized curve. If I don't go for that, I have to have a curve like this to classify it as a rigid connection. If it is falling here, the moment rotation, it is a semi-rigid. And if it does like this, it is a very flexible connection. So the problem here is we don't have procedure currently to understand with our grade of steel and our connection arrangement, or if we borrow the arrangement from 358, do we end up with a rigid connection, semi-rigid or flexible connection or not? Do we have the correct electrode? Do we have the, I mean, we are following the AWS formula for, AWS code, American Welding Society codes for even our welding procedure. Do we end up with a pre-qualified connection or not is also a question mark. So there is a lot to eat. The cake is huge for everyone in this country to research on steel, bring up more reliable connections with respect to these kind of steel connections. So things can be done a lot in this particular category. Now, these are all the available connections. Many of you practitioners might be using these connections in your PV structures or steel structures. Understand that, yes, look closely, this is eye to eye connection, and these pre-qualified connections are only major axis to where the beam applies moment about the major axis of the column. None is in the other case. Minor axis pe koi nahi hai. So you cannot consider as a rigid connection if the beam is connecting to the minor axis or the web of the column se attach hoega. Please don't consider as a rigid connection and go about your design and drift calculations, etc. These are all the connections that are there. Procedures are also there. What we can do is look at the procedure in which they have pre-qualified a connection and adopt the same to develop some connections for Indian people. So with respect to some studies that we have done with respect to grades of steel, base metal and all, we have done. A small study I want to highlight is with respect to what one of my MTech student had done, which is with respect to, we had two frames that were considered, one in which only peripheral moment frames are there, and one in which the redundancy is higher in Indian condition where we use all frames to be moment resisting frame. Now this has been analyzed only in X direction, because if I have to go for this Y direction, then there is no moment frame in Y direction at all. Then I have to go for another lateral force resisting system to do the actual design in the system. And what we did is we took different categories of 3-story, 6-story, 9-story, bay widths varying from 6 meter to 12 meter. And what we did is we looked at different aspects as to what the grade of steel. If I use, let's say RY value is 1.5 in one case, let's say I use an E250 grade. The average value of RY for E250 is 1.4. If you ask the manufacturer with respect to what are the different RYs you get, you may get a different kind of variation. You might get 1.6, you might get 1.2. It may vary because this 1.4 is a mean value. So what if this RY value, if I take it 1.5, what happens? And to understand the performance clearly, what we did is we modeled the non-linearity, which you have already done for RCC, the same procedure. I mean, to give you a flavor of performance-based design, as in the case, you follow the similar procedure. I think Tajul would have gave you an explanation with respect to 4117, etc. So in there itself, steel ke liye, RCC ke liye, whatever is given for non-linear hinges in 4117, the same is given for steel also, for beam, connection, panel zone and column. So whatever type of connection you choose, there are different rotation values given for different types of connections. So you can check them and give your model accordingly. Why I'm saying is, see, we have 4 elements: beam, column, connection and panel zone, right? If I model the non-linearity in these elements, because if I'm let's say I'm depending upon the non-linearity of the panel zone, then I have to think about the deformation due to the lower stiffness of the panel zone, the secondary effect that the panel zone might be giving into the overall behavior of the system. When I do the analysis, I cannot be doing that, okay, I'm depending upon the non-linearity of panel zone, but I'll not model panel zone in my beam moment frame for design, because then it will be a problem in terms of the reality as well as what you are modeling in this. So if you do beam, column, connection, and panel zone nonlinear property as given in 4117, and then you do an analysis, we had done a time history analysis, and you can look at column hinge, beam hinge, connection hinge, and panel zone we have measured. You can understand what is the problem is when I do a pushover analysis. We did pushover, this is a low-rise structure. So pushover analysis, I mean low-rise structure where the mode, the fundamental mode, lateral mode is a governing one. That is why we went for pushover analysis. And based on that, when we looked at it, you can see the first phenomena that is happening is panel zone yielding. Next one is column connection hinge is getting formed. Performance point is there, and then further only beam hinge is formed, which is not the ideal behavior that you would want. You would want the beam hinge to form first, then the panel zone yielding can happen. Column hinging should not have happened. So somehow using our demand, our seismic criteria, our loading criteria, our steel, and then using some kind of information, because we don't even have 4117 equivalent criteria to be given. So if we take that particular criteria, see there are some plus and minuses here and there with respect to our code and our understanding of steel, but it will take a very short amount for a large number of people to get together and get to develop this particular criteria, right? So when we did this analysis, we found that for across all models, all depth, this is the same phenomena. We are getting the connection hinging, panel zone hinging, but no beam hinging and all was not getting formed. But when I altered the improved connection, or if I alter the design in terms of if I change the connection, taking 1.3 MP for calculation of shear demand, I mean I increase the demand on the panel zone in comparison to beam. I mean the code says 1.2 MP leke, you use 1.2 MP to calculate the shear demand in the panel zone. Rather than that, if I do 1.3 MP, then suddenly my behavior changes. I get my beam hinging to be the first criteria that forms first, and then it moves on to the other kind of panel zone hinging. So that is what I want to say, that if you are doing, first of all, do the design correctly, using the correct sections, using the latest code, using correct material, and all the design procedure has to be done. Then you go after, if you're doing performance based design, you go after, we don't have a criteria right now in terms of moment rotation. Take 4117 itself. Why I'm saying so is because, see, 4117, if you open, it gives you a backbone curve, a monotonic backbone curve. Now you would ask me, in earthquake, it is only the cyclic behavior that is predominant. How come a monotonic curve is given? The 4117 curve is actually a derivation which is given as a monotonic curve, inclusive of the effect of cyclic effect that is coming into picture. So it is, how does a code give always the clauses? Whatever may be the actual capacity of the section, the clauses would keep you in a safe range to accommodate certain uncertainty. Same way 4117 में जो monotonic curve दिया हुआ है, it already includes the cyclic effect into picture. So it is a bit conservative. If you test a beam section, if you column section, whatever rotation your beam or column might have will be more than what the 4117 has. So till the time we know better about our material, it is okay to use 4117 for the time being in order to do your performance based design or your vulnerability analysis or your nonlinear time history analysis, etc. Right? With that, I think fun questions. If it had been an interactive or you were physically there, we would have talked about it. Here, the wrong thing is it's not acceptable because beam hinging is there and column hinging is at a unwanted location. If it was here, it would have been better, right? And the last one is with respect to this, is it acceptable? It is acceptable, but here there is a throw here that flexural hinge or such kind of a hinge, the support is pinned here. So you would not expect a hinge to form at that particular location. So just to have fun with you guys, I'd kept that particular slide there. So thank you very much. If you have any doubts, please let me know.
हेलो
Yes.
गुड इवनिंग सर सर मुझे आपने जो रिजल्ट शो किया है बेशियर और ड्रिफ्ट रेशियो में डिफरेंट परफॉर्मेंस पॉइंट जो आपने IOLS CP पे दिखाया तो मुझे वो ड्रिफ्ट रेशियो की वैल्यूज कैसे जैसे प्लास्टिक हिंज जो IO में आई है उस पर पर्टिकुलर डिस्प्लेसमेंट आया वो पुशओवर एनालिसिस से मिला तो उसके ड्रिफ्ट रेशियो वैल्यूज कैसे निकालते हैं?
नहीं, IOLSCP का जो रेशियो आपको दिया गया है, लाइक आप कोड देखते हैं 4117 या कोई और कोड फीमा का कोड देखते हैं,
Yes,
तो
sir.
ये जो IULSCP है, sometimes they give in terms of rotation or sometimes they give in terms of drift value. So you have to kind of manage with respect to कि E-tabs जैसे अगर आप सॉफ्टवेयर यूज करके ही कर रहे होंगे,
Yes,
you
sir.
can define these limits inside there as to what your IULS. I mean IULSCP is not a hard line कि पत्थर पे लिखी लकीर नहीं है कि वही वैल्यू होना चाहिए जो कोड में लिखा है.
Yes, sir.
Based on your building and your functionality, you can change that particular value and you can define it in E-tabs. And the E-tabs itself kind of shows it to you as to when it is forming based on the rotation of the member.
Okay, sir. Sir, that's fine. मुझे ये पूछना, ग्राफ में जो ड्रिफ्ट रेशियो वैल्यू तो उसमें नहीं देता है ना?
नहीं, आपको सेपरेटली उसके डिफ्लेक्शन के वैल्यू लेके इंटरस्टोरी ड्रिफ्ट रेशियो आपको कैलकुलेट करना रहता है.
यस सर, कैलकुलेट करना है. जैसे आईओ पे मेरा 183 या 200 वैल्यू आई डिस्प्लेसमेंट की पुशओवर एनालिसिस से किसी स्टेप पे, तो उसको हम स्टोरी जो ड्रिफ्ट की डेफिनेशन होती है वो दो स्टोरी के बीच में डिफरेंस अपॉन स्टोरी हाइट होती है.
स्टोरी.
तो उस ग्राफ में जब हम पूरे स्ट्रक्चर की बात कर रहे हैं,
आपको इंटर स्टोरी के बेसिस पे आपको जाना पड़ेगा. सी आपका हिंज जो फॉर्म हो रहा है, IULSCP का डेफिनेशन जो है पुशओवर कर्व में जब आप देखते होंगे, the first yield when it happens when one of the members yields, right?
yes,
आप अगर देखोगे कि वो यील्ड का जो डायग्राम है वो एक जगह जब यील्ड हो जाता है तो द ड्रिफ्ट चेंजेस एंड देन रेस्ट ऑफ द लोकेशंस कई मल्टीपल जगह पे हिंज बनता है. So you will have to look at each individual members also as well as look at interstory drift ratio. See, don't go as per the format of what the code says. You have to look at कि अगर आपको energy dissipation totality में चाहिए, तो you have to look at the member level energy dissipation also, right? कि total मेरा कितना energy dissipate हुआ.
yes,
One way is perform 3D जैसा सॉफ्टवेयर जहां देता है. I mean you have to do excess calculation in addition to whatever the E-tabs gives or whatever your hand calculation gives. Perform 3D जैसा सॉफ्टवेयर आपको कैलकुलेट करके दे देता है कि टोटल एनर्जी कितना डिसिपेट हुआ. जो इंटरस्टोरी ड्रिफ्ट रेशियो की आप बात कर रहे हैं, इट हैज टू बी कैलकुलेटेड नॉट जस्ट एट दी अभी पुशओवर कर्व का जो लैंग्वेज है, इट सेज टॉक्स अबाउट ओनली टॉप स्टोरी एंड द बॉटम, राइट? इट डज नॉट टॉक अबाउट इंटरस्टोरी at intermediate level.
yes,
So you have to look at that aspect also. So don't follow a set pattern in terms of what the code or this thing is giving. Try to assimilate all the values. कि मेरा अगर मैं IULSCP, can I define it at a beam level? If I define it at a beam level, how do I get its performance from my analysis results? How much rotation has it undergone? Is it as per my IULSCP that I have defined or not? उसके basis पे भी आप अपना analysis कर सकते हैं.
yes, sir.
I understand you have to kindly go through once I share this slide and everything, kindly go through it once again and write to me.
सर मुझे वो ग्राफ में जो ड्रिफ्ट रेशियो की वैल्यूज आ रही थी वो नहीं समझ में आ रही थी कैसे आ रही, जैसे बेशेयर जो पुशओवर एनालिसिस से आई.
It is pushover. If I look at that particular graph, it is जो रूफ का ड्रिफ्ट है ना,
yes sir,
उसके बेसिस पे लिखा हुआ है वो वाला.
okay, roof drift, yes sir.
रूफ ड्रिफ्ट के बेसिस पे.
Okay,
That is why
thank you sir.
pushover only works if it is like first mode ही आपका govern कर रहा है करके. Don't use pushover in a very generous way.
Okay sir.
Yeah.
Thank
Yes, Dr. Narayan.
गुड इवनिंग सर.
जी
सर मेरे को सर IS 800 से रिलेटेड कुछ पूछना था और सर और भी क्वेश्चंस है सर. सर IS 800 2007 टेबल 10 पेज 44 पे सर जो हमको क्लास A क्लास B वो सब जो डिफाइन करना होता है, and in that for I section we have A B C D all 4 sections, and when we take H by V greater than 1.2 we consider it as a class A, and for less than 1.2 it goes lower
Dr.
than
Narayan,
that.
one second here. Can you send this question to me because it is not directly pertinent to what we have discussed today, right? It is with respect to a particular member design, right?
Yes sir, related to class A class B.
Correct, but ये जो class है, is it that plastic semi compact वाला class नहीं है ना ये?
No sir.
That's what. So if you can ask, you can send me this question within a day itself, I'll give you a reply back. Can you keep your questions to what we have covered today in terms of IS 18168 capacity design and the kind of deformation control and force control element?
Yes, sir. Yes, sir. Sir, the effect of local buckling on rotational capacity, sir, means we said that local buckling affects the rotational capacity. So, means in what manner, sir, it is
See,
affect?
you understand that in steel structures, rather than strength के अलावा serviceability तो हम normally check करते हैं. Stability is a problem for steel structures, right?
Yes,
The
sir.
member can undergo global buckling, the member can undergo local buckling. आप जानते हैं कि whenever a member undergoes global or specifically local buckling, in terms of a member which is subjected to cyclic loading, what happens is suddenly, rather than the strength exceeding a certain value, the member undergoes twist, torsion, or deformation, lateral deformation, etc., without the load getting increased. So there is a sudden dip that happens. So if I have local buckling that is enhanced due to lesser thickness of a flange or a web, suddenly what happens is, even though my section would be कि आपने शुरुआत में calculate किया होगा कि मेरा demand 3000 kilonewton का है, kilonewton meter का है, my section would be capable of carrying a 4000 kilonewton meter because of its higher depth. But once non-linearity comes in, once local buckling comes in, it may achieve MP, but when larger rotation comes in, when more inelastic deformation happens, the local buckling phenomena happens too large that the beam stability it loses, and it loses its load carrying capacity. So that is the main issue.
Yes, so the previous question I asked actually was related to this question only, so I could not complete that. So, sir, in that the criteria is depending on the flange thickness, not the thickness of web. So actually,
no, both are there. Dr. Naran, if I interject, if you look at the code table 2 in terms of classification of
yes,
the section,
table 2 is there.
And if you have already understood that if beam is my deformation controlled element where the plastic hinges has to form, then the beam section should be surely plastic section.
Yes,
right?
sir.
If you want plastic section, then go to table 2 of either IS 800 or IS 18168. It has criteria for both the flanges and for webs, right? Because
Yes,
think of the same case that if my nonlinearity is happening at the plastic hinge, you saw that flaking of the this thing, right? The whitewash. So it is encompassing the area of flange as well as the web of the section. So both are undergoing deformation. So either one of them, if they undergo local buckling, I mean, you must have heard of the term crippling, local buckling of the web and all.
Yes,
that happens under static load itself, right? If there is a concentrated pointed load, you have such kind of phenomena. If you have a cyclic load that is happening, even this can happen if you use a very thin web. So if you check that code, it gives you criteria for both web and flange.
Yes, sir, it gives. Table 2 gives, sir, but table 10 doesn't discuss
no,
about.
But then what criteria satisfies is table 10, you have to keep it separate, but then the final section, when you provide, it has to be a plastic section in totality. It cannot be that is what I said. If your flange is plastic and your web is compact, what would you call that section?
Compact.
It will not be correct. So that way you have to go about your design.
Sir, in India, sir, we weld the flanges and bolt the web section. So,
yes.
Yes, sir. So I could not get the general perspective of that, means why they are doing this.
No, why they are doing this in a sense?
Means
no,
why not welding?
Okay, this is with the understanding that, see, first of all, one thing is the web, we have a general notion, and it is not very wrong, that web transfers shear and flanges transfers the moment.
Yes.
Right? You can do welding also, you can do bolting also of that particular section that is there. Right? The easiness of connection is what comes into handy. So if you say, if I have to weld a beam to a column at the site with the web also getting welded, that is an on-site welding, right? Which one would not prefer in totality. Nowadays, we don't want any kind of on-site welding to happen. So in that case, and the availability of कि मेरे पास cleat angle है, bolt hole already है, welding करने से पहले I have to keep the beam at position, right? So before even putting a tack weld or something, if I can directly bolt it, then it gives me easy proposition for kind of welding the flanges at the top. So it is nothing to do with design being better than one above the other. It is about easiness of working that majorly governs.
Yes, sir. Yes, sir.
Right?
Can I ask sir one more question, sir?
Yeah, sure.
Sir, regarding the sir plastic sections and compact sections in IS 800 2007, the definition given is that plastic section will undergo the whole inelastic rotation and it will go till MP, but compact section will have the MP but will not have the complete plastic rotation. So what is the level of rotation that compact section will be going? Means how we will decide that it is going, how much
I see
rotation capacity?
that is where you have to test the section. See how come these H by T and B by T ratios have come about is with respect to testing those sections. So what they have done is, if I use a particular criteria, let's say form an equation, and the flange thickness is coming 16 mm and the web thickness is coming 12 mm. I do a test in which the beam is plastic hinge is getting formed, and I look at the rotation capacity that is there. My requirement also already said that, okay, if it achieves more than 5% story drift ratio, the connection is working absolutely fine, right? That is my minimum requirement. So if that is getting achieved by a particular section, obviously that would be a plastic section. But if you go for a thinner section and suddenly during the test you find that instability is coming into picture, so compact sections are all those sections where the thickness are not adequate, that it is adequate enough to allow the formation of the plastic hinge. Every fiber at one particular location is getting yielded, but when it tries to rotate further, instability is coming in terms of local buckling of the member. So people have done simulations and tests and then come up with these stringent values. So if you look at earlier code, there would be some value of, even in American code, there would be some value that there would be there earlier, which in a different era, it would have changed to a more stringent value. And you can see that this is going on into a stringent value in order to achieve more and more kind of stable, or what do you say, plastic section, more amount of rotation you want, more thicker section you need to use. That is, so it's getting stringent only. So whatever data you want to have, whether it is brace, link or column or beam, you have to test it and find out its property.
Sir, in
Right?
section 9.3, sir, they have taken both plastic and compact in one particular section, and semi-compact as different. So in semi-compact, they are using beta MP. So that is converting into ZE. So that is converting to
Elastic modulus.
elastic modulus.
Correct.
But for
If you,
plastic and compact, they are using the same MP. So they are considering.
correct. Strength wise, see, think in strength wise, both will reach MP.
Yes, sir.
But one guy has a higher rotational capacity and the other one does not have. But that doesn't change the full capacity of the strength of the section. So that way MP is correct there. But if you look at the semi-compact section, which you see that key, after the yielding extreme fiber ek bar ho jata, which is the point where we say that the system has yielded or the member has yielded, us point ke baad it doesn't go reach up to MP level. So that is why there ZD comes into picture.
Sir, MP is not reaching and rotation is not reaching, MP is reaching in compact. So that
See, there is strength and there is rotational capability, right? A beam, if I keep on loading, it will reach a particular strength and it will also rotate alongside with that, right?
Yes, sir.
Whether it is in elastic stage, whether it is in non-linear range, any which way it is going to perform. But when I load a beam and it reaches plastic moment capacity, you can calculate by hand and you can verify through experiment also that whether it has reached the MP value or not. Or you can do strain gauges at different levels and kind of measure whether that is getting formed or not.
Yes.
Now the thing is, let's say the section has reached the MP value, which means all fibers have yielded at one particular location. Now, are you telling me that I cannot load it further?
No, sir.
I can load it further. The load may remain the same. It may not change. If I consider strain hardening everything into picture, but the beam without going into any instability can rotate without decrease in the strength value. That is the rotation capacity that I'm talking about. So that a plastic section can do, but a or a compact section cannot do. It will undergo local buckling very quickly, right after achieving the plastic moment capacity. So if you check for strength, both are achieving MP, but one guy can achieve rotation, higher rotation at that same load value for a larger deformation angle. That is the case.
Yes. Yes.
Right.
Thank you.
Okay. Okay. Mansimran Singh.
Hello, sir. Good evening.
Good evening.
Sir, I wanted to ask the question in the slide which you showed the conclusions, the first conclusions actually.
That is with respect to that study, right?
Yeah, in which the lesser span was having 20% less tonnage, and when we increased the span to like a bit more, it was giving the same results. I wanted to know that how this situation arrives, because in one case, I think you have considered that peripheral
Correct.
frames are only having the earthquake resisting capacity or the lateral load system.
Correct.
And in the second study, the internal frames are also the lateral load resisting systems.
Correct.
Now,
please complete.
So now there are two things, that how we can segregate that our peripheral frames only will behave as lateral load resisting systems and internal frames will not carry any lateral load. First thing is this is my question.
Okay.
And the second thing is that the criteria of that span depth I mean, like there was like 6 meter span and there was one more
span.
Yeah, in the 12-meter number.
So with respect to your first question, this is true for moment resisting frame and concentrically braced frame, which we'll discuss later on. It is like the code gives you a kind of freedom in terms of choosing how much a particular lateral force resisting system has to take up a certain load, earthquake force. So when you, the whole thing depends upon key by just saying that, okay, the peripheral frames are going to take the 100% of the lateral force will not work unless the interior frames are modeled in such a way, right? So what we do during modeling is, let's say the X direction. If you remember the moment frames that were there stacked up one below the other in terms of the plan of this thing. If I choose the peripheral frames as the ones that I have to design, what I have to do is, for the internal frames to carry gravity, it should not take part into the lateral force effect. How can I do that? Can you suggest me a way in which, how can I not allow the interior gravity frames, which are calling that they are only taking part in gravity, but not in lateral? How can I ensure that while modeling in ETABS or STAD?
So we
let's
have
say beam.
to,
Let's say beam, if I say I don't want it to take part in any lateral force.
So we have to release it.
Correct. Absolutely correct. So you have to give moment release at the ends of the beams, such that when the columns move, the beam does not take part in lateral force effect.
Yes.
So here when you do, there is one part, okay, you can release all the interior beams. You can keep all the peripheral frames as the moment frames, then do an analysis. But here, one point comes in, all the columns are then cantilever columns. You can also give moment releases partially for the time being, so that you can totally assess what is the exact demand that is coming, and then you assess the demand on the peripheral frames. But you can also do it in a way, okay, cantilever column liya, it may not be total 100% to peripheral, some amount might be taken by the interior columns also.
Yeah.
But kindly ensure that once the design is done, then you give the release as such, whatever moment release you aapne diya hai, whether it's a shear connection ke through, simple connection ke through, you provide the same thing in the actual structure also. Otherwise, then the problem comes, your internal frames will also take lateral force, which is not meant to, and it will fail there.
Okay.
The second question was?
Second question was, sir, was कि उसकी एक की जो framing है, the span is 6 meter and the other is having 12 meter.
Why I took 6 to 12 was, if you look at literature, they mention that the same as the case for 3 to 8 meter span for RCC, that after 12 meter, the section size becomes uneconomical. Whereas less than 6 वाले section size अगर आप span लेते हैं beam के लिए, तो then shear वाला criteria govern करना शुरू कर देता है flexure के against.
Yeah, because the stiffness reduces.
Correct. So that is why it's a benefit that for a steel structure we can go up to 12 meter span. That gives us enough column free spaces. वो सारा benefit रहता है. But if you go beyond 12 meter, then unsymmetrical or unsymmetrical नहीं, uneconomical sections. आ जाए.
Yeah, their moment capacity has to be increased a lot.
Right, right.
Okay, sir, इसमें एक question है कि whenever the earthquake is coming, वो ground की acceleration होगी, उसके बाद मेरे जो internal columns हैं वो भी उसी acceleration के साथ move करेंगे और जो मेरे periphery के columns हैं वो भी उसी acceleration के साथ move करेंगे.
Correct.
In that sense, how can I say कि मेरे जो peripheral columns हैं वो earthquake load को ज़्यादा bear करेंगे और
नहीं, one thing correct, if you remember कि आप जब भी like if you have designed a particular building or something like that, if you give a shear wall at the very edges or anywhere, before the shear wall and after the shear wall, you will find that the stiffer member जहाँ पर है वहाँ पे ज़्यादा attraction of forces आ रहा है. It's a common rule. So when you have peripheral frames that is being given, the majority of the forces will flow into that particular area. Now, having said that, the whole tone, आप rigid diaphragm दे रहे होंगे, like if you are giving, if there are less
आपकी आवाज कट गई
holes.
बीच में से.
Okay, can you hear me now?
Yeah, I can hear you now. वो shear wall तक का point समझ आया, उसके बाद
shear wall तक का point आया, तो when I give a peripheral RC frame at the peripheral, it has larger stiffness than the internal frame because internal frame का section size is only governed by gravity, whereas the peripheral one is governed by both gravity as well as lateral. So उसकी वजह से सारे forces वहाँ flow करेंगे. One additional thing that you are doing as a designer is either you are using की cutouts कम है तो rigid diaphragm का action आप लेता है. इसके हिसाब से आपका जो पूरा columns है, every node on the column, every node on the top of particular that slab will move equally in one direction. So what happens is कि जितना आपका stiff member है, that will govern the kind of P delta का जो effect आएगा, secondary effect आएगा, that is also governed by this particular stiff member that is going to come. Unless कि if your span is too large, जैसे अभी मैंने peripheral जो है 3-4 span के बाद 3-4 frame के बाद मेरा peripheral आया था. If it is a large building, then you may need intermediate frames also. It may not be enough कि that deformation compatibility is getting satisfied in that sense. But if it is a very small building, then the total deformation इसी peripheral के governing के साथ हो जाएगा. And if you do that compatibility kind of analysis, 3D analysis आप कर रहा है, तो everything is well and good.
Okay, so this can be considered as an analogy जो हम gravity moment frames कहते हैं in RCC.
Okay, हाँ.
वो भी
no, you cannot go with right now with the system that की if your internal frames are gravity frames only, then it should not be kind of a moment frame.
Yeah.
So it cannot be called as a gravity. I mean, in a low seismic region, yes, anything works. In a high seismic region, you have to assign properties or assign jobs to different frames. कि आप ये करेंगे, and you will do this job.
Okay, got it. So in conclusion, we can say that this is not 100% load is not being transferred only to the peripheral frames. There is some percentage of lateral force being transferred to the internal frames also. But
if the column is cantilever, if it is modeled as a cantilever, it will flow inside. If everything is kind of pinned करके कर रहे हैं, तो model wise it will go there. But yes, in reality, something will flow. But majority will flow to the peripheral itself.
Sir, what exactly does we mean by the cantilever column?
Cantilever column का मतलब ये कि जैसे अभी मैंने बोला कि beam को मैंने moment release किया.
Exactly,
right?
yes. Yeah.
But my column I'm not moment releasing, let's say, which means it is like peripheral from frames along with one total length of column which can carry bending moment. I didn't release any moment release. I didn't do any moment release in the columns, right?
Okay.
The columns may be subjected to lateral forces. Point loads आ रहा होगा. Moment तो beam से moment तो column पे transfer नहीं होगा.
Yeah.
But some lateral effect might.
Okay.
Some lateral effect might come on the column, so I'm calling it as a cantilever column.
So now there is a necessary case that my support has to be fixed in these cases.
Correct. I mean, it depends upon the modeling procedure. You can give it pinned or fixed. Yes.
Okay. Thank you.
Thank you, Mansimran ji. Anand.
Hello, sir.
Good
sir,
evening.
Nanta,
Sir.
hello.
Nanta, can you? Nanta, I'll come to you. First, let me answer Anand, who has raised his hands. Then I'll come to you.
Okay, right. So actually, sir, the same question relevant to one single. Actually,
Okay.
what you are saying is cantilever column. I think it should be called as propped cantilever, right?
A propped cantilever in the sense your beam
So
at the
it is
top
like,
is not.
shear kind of support is there at the top, and it is fixed at the base. Then shall we call it as a propped cantilever?
Maybe you can call it, because at the top, even though the beam is hinged, but the overall the behavior can be like that. But even propped may not be the right word. I mean, pardon me for saying cantilever, or pardon all of us in calling it as a propped cantilever, but you get the idea of how to model it and then go about the design.
Right.
Once you do the design, check the base shear as how much the proportion. I mean, you have the total quantity as to what the total base shear was and how much proportion peripheral takes in, how much column takes in. Then you can find out that you might have designed for 100%, but 80, 85 is what the number you end up with.
Right.
You don't know how. Yeah. So
right.
some changes will be there. Yeah, Anand.
Right.
Okay.
Sir. Thank you, sir. Okay. Thank you.
Yeah. Anand.
Good evening, sir. Thank you for this exhaustive session. I have one query on slide 27. You are mentioning that there are some lateral ties are required to the beam. So will you again go to the slide 27?
1 second. Yeah, this one, right?
Right. Yeah. See, here I have a couple of questions. See, here basically this is a typical arrangement, which is a you can say a very specialized arrangement. But in normal practice, we don't find this arrangement actually because of various reasons. So how to take care of this?
See, this is just to show as to what is the concept of attaching the top flange and bottom flange. In reality, what would happen is you would have a deck sheet which is having a limited width of, let's say, 1.5 meter and a length of, let's say, 4.5 meter. Right? Your span may be 9 meters totally. So you know that since the deck sheet is one-way slab, so after 4.5 meter, you need a secondary beam. Right? So that secondary beam can be the first location where your primary beam at the other end, the perpendicular end, can have some connection with the secondary beam. Right? Now, other than that, on this direction where the deck sheet is going, where the width is coming, you don't need any requirement of secondary beams to carry the deck sheet. But the criteria for lateral torsional buckling may come into picture at some point for the 9 meter beam, which is carrying some vertical load, whose IX is more than IY, all those criteria which pushes a beam into a lateral torsional buckling range, like possibility. There, a secondary beam, I mean, what we do normally in India in practice is through secondary beams, we attach the top and bottom flange. We don't need such a kind of elaborate kind of arrangement where we have to do so many things here. This may be a typical case that I had taken from what I found from the net. But in our case, secondary beam is more than enough to cater for this particular effect. But yes, you have to check your primary beam, whichever is there, for lateral torsional buckling, and accordingly provide this particular support. Sometimes one more thing I want to add here is sometimes the concept comes in as the shear stress that is there with the deck sheet also provide some restraint to the top flange, which is under compression. It is the compression flange which undergoes the buckling and which promotes the the lateral torsional buckling. But when you consider a case of earthquake loading where the top flange and bottom flange can undergo tension compression, reversal can come. That cases you have to pick both the flanges and arrest them by secondary beams or by such kind of means.
So, okay, now there are two sub questions.
Yeah.
See, one is in normal practice, either we go with some plan bracing, or if it is RCC deck slab, then usually we don't provide anything. It is just a deck slab with some shear studs, and at the end, especially near the column, as you mentioned that if there is a tension at the top, then that particular restraint will not be useful. So in that case, the secondary beams running in other direction for some reason, if they are available, then nothing like it. But if they're not available, then you mean to say we should provide.
We should provide.
Okay.
We should provide because it is the requirement of the beam in terms of lateral torsional buckling that is there. So we should provide.
Okay. And one more thing, see, in some of the literatures, what I've seen that a vertical stiffener plate is also sometimes considered as a giving some lateral restraints. So I don't
Correct.
know. Yeah. So if that is available,
even
then
gusset plate that are provided between beam column joint also provides restraint. It gives additional rigidity to the beam column joint. So anything that we add has some kind of effect overall on the different load transformation or division.
Okay.
So the best case scenario is we have a current code that we have to follow.
Okay.
But yes, more research has to be done in order to understand the effect of different plates. Stiffener भी हो या गजट प्लेट भी हो उस हिसाब से.
Right, right. Now, इसमें there are further sub questions. See, in one of the slide you mentioned local buckling and global buckling.
Correct.
So local buckling, the stiffener may be useful from local buckling, but
Correct.
from global buckling point of view, how to take
You're right.
Then
नहीं,
that
global buckling के लिए lateral bracing is the better option. In terms of let's say column का 12 मीटर का height है तो you provide a lateral bracing at a mid level, even if there is no slab there, right? Normally when you design an industrial structure,
right,
you break the height of the column by giving horizontal bracing to reduce the height. The same applies for a beam also. कि अगर आपका length बढ़ रहा है या कुछ बढ़ रहा है तो by providing lateral bracing वही है global buckling को control करने के लिए. Stiffness might, as you said, stiffness might not help.
Okay, but in this case, do we need this bracing on both the flanges, or it is because usually what we see is only one set
see,
of bracing.
understand one thing ki, to avoid instability like lateral torsional buckling, if you understand the behavior, let's say if it is only under gravity load, shear studs are more than enough.
Okay.
If it is under a seismic criteria, yes, we have to hold both the things, or as I shown in that particular diagram, that the loading conditions are as such that the beam bends in double curvature.
Okay.
Then there is a requirement at that location where that point of inflection is coming, you have to give supports at both top and bottom.
Okay.
Yeah.
Got it. Thank you, sir.
Okay. Thank you. I think I'm sorry, first of all, ki it was an exhaustive session. Next week, we'll cover braces and EBF systems. If you have any doubt, kindly send me the queries. I'll have to stop the session now as I have a train to catch at 6:45. So I'll have to leave right now itself. So thank you to everyone for interacting. Any doubts are there, please send directly a mail to me on my official email ID. I'll try to reply to you as soon as possible. See you all next week, next Saturday, where I'll cover the design procedures for CBF, which is little bit difficult or little bit complicated. Once you understand that, EBF would be absolutely simple. So that way we'll cover all the basic design. And then based on that, you will be very much free to do any performance-based design or any analysis. Thank you, everyone. See you all next week.
Thank you, sir.
Thank you.
Hello.